Look up at the night sky. What you're seeing isn't real. At least not in the way you think it is. The light from those stars has been traveling for so long that by the time it reaches your eyes, the stars themselves might already be dead. You're looking at ghosts, cosmic ghosts frozen in time, their light still racing across the universe long after they've exploded into oblivion. This is where our journey begins. Not with answers, but with questions that will reshape everything you thought you knew about reality itself. The universe doesn't care about your common sense. It doesn't care that you were taught in school that time flows in one direction, that space is empty, or that we live in 3 dimensions. The cosmos operates on rules so strange, so counterintuitive, that even the brightest minds in physics sometimes struggle to believe their own equations. Let me tell you about the multiverse. Not the comic book version. The real one. The one that might actually exist. Right now, as you listen to these words, there could be infinite copies of you living out every possible variation of your life. In one universe, you became an astronaut. In another, you never learned to read. In yet another, humans never evolved at all. The multiverse theory suggests that every quantum decision, every random fluctuation in the fabric of reality, spawns a new universe. It's called the many worlds interpretation, and it emerged from quantum mechanics itself. Here's what's wild. When scientists first discovered quantum mechanics in the early 20th century, they noticed something impossible. Particles don't have definite positions until you observe them. Before measurement, an electron exists in what we call a superposition, occupying all possible states simultaneously. Schrödinger's cat, both alive and dead. The famous thought experiment wasn't meant to explain reality. It was meant to show how absurd quantum mechanics seemed. But the absurdity turned out to be true. Hugh Everett III proposed a solution in 1957. What if the particle doesn't choose? What if, instead, the universe splits every time a quantum measurement occurs? Every possible outcome happens, but in separate, non-interacting universes. You measure the electron here, it's spinning up. But in another universe, equally real, it's spinning down. Both universes exist. Both are real. You just can't see the other one anymore because you've been split into 2 versions of yourself, each unaware of the other. The implications are staggering. If the many worlds interpretation is correct, then every decision you've ever made, every dice roll, every genetic mutation has created branching realities. The multiverse isn't some distant phenomenon. It's happening right now, billions of times per second, splitting reality into an ever-expanding tree of possibilities. But wait, it gets stranger. The multiverse might not just be about quantum mechanics. It might be baked into the structure of space itself. In the late 1970s, a physicist named Alan Guth proposed something called cosmic inflation. In the first fraction of a second after the Big Bang, the universe didn't just expand. It exploded outward faster than the speed of light, growing from smaller than an atom to larger than a galaxy in less time than it takes light to cross a single proton. Inflation explains a lot. It explains why the universe looks the same in all directions. It explains the smoothness of the cosmic microwave background radiation. But it also predicts something extraordinary. If inflation happened once, it might never stop. Not everywhere, not all at once. Instead, inflation could be eternal. In some regions of space, inflation ends and a universe like ours forms. But beyond our cosmic horizon, in regions we can never see, inflation continues forever, spawning bubble universes like champagne bubbles in an infinite ocean of expanding space-time. Each bubble is its own universe with its own laws of physics. In some bubbles, gravity is stronger. In others, electrons have different masses. In some, the fundamental forces are arranged in ways that make life impossible. We happen to live in a bubble where the laws of physics allow stars, planets, and eventually consciousness. It's called the anthropic principle. We observe the universe we do because we couldn't exist in any other kind of universe. The cosmos isn't fine-tuned for us. We're fine-tuned for this particular bubble of existence. Think about that for a moment. Our entire observable universe, everything we can see with our most powerful telescopes, everything that light has had time to reach since the Big Bang, might be just one bubble in an infinite froth of bubble universes, each with its own unique physics, its own version of reality. And we'll never see beyond our bubble. Ever. The expansion of space ensures that regions beyond our cosmic horizon are receding faster than light can travel. They're permanently cut off from us, existing in a realm we can never explore, never confirm, never even glimpse. This is where physics starts to sound like philosophy. How do we test a theory if the evidence exists beyond our reach? Some scientists argue that the multiverse is untestable and therefore not science. Others counter that if a theory makes predictions we can test in our universe, and those predictions turn out to be correct, then we should take seriously what else the theory says, even if we can't directly observe it. We believe in black holes, even though we can't see inside them. We believe in the Big Bang, even though we can't rewind time to watch it happen. The multiverse might be in that same category, a consequence of well-tested theories that points to something vast and invisible. Now let's talk about something even more mind-bending, the holographic principle. This one sounds like science fiction, but it's deadly serious physics, and it might be the key to understanding reality itself. Imagine you have a black hole. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. For decades, physicists thought black holes destroyed information. Anything that fell in was lost forever. But in the 1970s, Stephen Hawking discovered something shocking. Black holes aren't completely black. They emit radiation. They evaporate. Over vast stretches of time, a black hole radiates away all of its mass and disappears. This created a paradox. If black holes evaporate, what happens to the information about everything that fell in? In quantum mechanics, information can never be destroyed. It can be scrambled, hidden, or transformed, but it can't vanish. This is called unitarity, and it's a fundamental principle. Hawking's calculations seemed to violate it. Information fell into the black hole evaporated, and the information was gone. The paradox tormented physicists for decades. The solution came from an unexpected place: string theory. In the 1990s, physicists working on string theory realized something profound. All the information about what falls into a black hole might be encoded on its surface. The event horizon, the boundary of no return, acts like a hologram. Just as a two-dimensional hologram contains all the information needed to recreate a three-dimensional image, the two-dimensional surface of a black hole contains all the information about the three-dimensional volume inside. This led to a radical idea. What if our entire universe works the same way? What if everything you see, everything you experience, all the three-dimensional space around you, is actually encoded on a distant two-dimensional surface? You're not living in 3 dimensions. You're living in a projection, a hologram of information stored somewhere else. The universe is a hologram and we're the image. This isn't just wild speculation. The holographic principle has mathematical support. It appears in string theory, in loop quantum gravity, in calculations about black holes and the Big Bang itself. Some versions suggest that the information is encoded on a surface at the edge of the universe, billions of light years away. Others suggest it's encoded on surfaces called ADS branes in higher dimensional space. We don't know which version is correct, or if any of them are. But the mere fact that serious physicists take this seriously tells you how strange our universe really is. You might be a hologram, a pattern of information projected from a distant surface you can never touch, never see, never even comprehend. And you'd never know the difference because the hologram is perfect. It contains all the complexity, all the detail, all the richness of experience that you associate with three-dimensional reality. The hologram is reality, or at least, it's the only reality you'll ever know. Let's shift gears. Let's talk about time. You think you understand time. It flows forward. The past is gone. The future hasn't happened yet. And you're living in this thin slice called the present. But physics tells a different story. In Einstein's theory of relativity, time isn't a universal river carrying everything forward at the same rate. Time is relative. It depends on your speed and the strength of the gravitational field you're in. Travel fast enough and time slows down for you relative to someone standing still. Get close enough to a black hole, and time dilts so much that you could watch the entire future of the universe unfold while you age only a few minutes. This isn't theoretical. We've measured it. GPS satellites orbiting Earth experience time slightly differently than we do on the surface. If we didn't account for relativity, your GPS would be wrong by miles. But here's where it gets really strange. In relativity, the past, present, and future all exist simultaneously. Imagine space-time as a four-dimensional block. Your entire life, from birth to death, is a continuous path through this block. You experience it moment by moment, moving forward through time. But from the perspective of the universe, all moments exist at once. The dinosaurs are still roaming the Earth in the region of space-time they occupy. Your future self is already out there, somewhere further along the timeline. The block universe theory suggests that free will might be an illusion. If the future already exists, then your choices are already made, already written into the fabric of space-time. Not everyone agrees with this interpretation. Some physicists argue that the flow of time is real, that the future is genuinely open. They point to quantum mechanics, where the future isn't determined until measurements collapse the wave function. They point to the second law of thermodynamics, which says that entropy, the measure of disorder, always increases. Time has a direction because the universe moves from order to chaos, from low entropy to high entropy. The Big Bang was a state of incredibly low entropy, and ever since, the universe has been spreading out, cooling down, becoming more disordered. That's why you can't unscramble an egg. That's why you remember the past but not the future. Entropy gives time its arrow. But even this raises questions. Why did the universe start in such a low entropy state? What set up the initial conditions of the Big Bang? Some theories suggest that before the Big Bang, there was another universe collapsing inward, reaching maximum compression, and then bouncing back out in a big bounce. The Big Bang wasn't the beginning. It was just the latest cycle in an eternal sequence of expansions and contractions. Other theories suggest that quantum fluctuations in a pre-existing multiverse gave rise to our Big Bang. The universe wasn't created. It emerged. We don't know, and that's okay. Science thrives on not knowing. It's the engine that drives us forward. Every answered question reveals 10 new mysteries. Every solved puzzle exposes deeper layers of complexity. The universe doesn't give up its secrets easily. Let me tell you about dark matter. In the 1930s, an astronomer named Fritz Zwicky was studying galaxy clusters, massive collections of galaxies bound together by gravity. He calculated how much mass should be in these clusters based on the galaxies he could see. Then he calculated how much mass there had to be based on how fast the galaxies were moving. The numbers didn't match. The galaxies were moving too fast. According to his calculations, there had to be far more mass in the cluster than he could see. He called this invisible mass dark matter. For decades, astronomers thought Zwicky was wrong. But then Vera Rubin studied the rotation curves of galaxies in the 1970s. Stars at the edges of galaxies orbit the galactic center. If most of the galaxy's mass is concentrated in the center, where the stars are densest, then stars at the edge should orbit more slowly, just like outer planets in the solar system orbit more slowly than inner planets. But that's not what Rubin found. Stars at the edge of galaxies orbit just as fast as stars near the center. It's as if there's a massive halo of invisible matter surrounding each galaxy, pulling the outer stars along faster than they should be moving. Today, we know that dark matter makes up about 85% of all the matter in the universe. Everything you can see, every star, every planet, every galaxy, every cloud of glowing gas, is just the tip of the iceberg. The vast majority of matter is invisible, interacting with normal matter only through gravity. We've mapped dark matter across the universe by watching how it bends light from distant galaxies, a phenomenon called gravitational lensing. We've detected its gravitational influence on the cosmic microwave background radiation. We've simulated the formation of galaxies in supercomputers and found that without dark matter, galaxies like ours wouldn't exist. But we still don't know what dark matter is. It's not normal atoms. It's not black holes or neutron stars or planets. It's something else entirely. Physicists have proposed dozens of candidates. Maybe dark matter is made of WIMPs, weakly interacting massive particles that barely interact with normal matter. Maybe it's axions, ultralight particles that formed in the early universe. Maybe it's primordial black holes, tiny black holes created in the Big Bang. Or maybe our understanding of gravity is wrong, and what we call dark matter is actually a modification of gravitational laws on cosmic scales. We're searching for dark matter in deep underground laboratories, where detectors wait in silence for a dark matter particle to collide with normal matter. So far, nothing. We're creating dark matter in particle accelerators, smashing particles together at near-light speeds to see if dark matter emerges from the debris. So far, nothing. We're scanning the skies for signs of dark matter annihilating itself, producing gamma rays or other signals. So far, nothing. Dark matter is elusive. It surrounds us, holds galaxies together, shapes the structure of the universe itself, and yet it remains invisible, untouchable, unknowable. And then there's dark energy. If dark matter is mysterious, dark energy is incomprehensible. In the late 1990s, astronomers were measuring the expansion rate of the universe by observing distant supernovae, exploding stars so bright they can be seen across billions of light years. They expected to find that the expansion of the universe was slowing down, gradually decelerating due to the gravitational pull of all the matter in the cosmos. Instead, they found the opposite. The expansion of the universe is accelerating. Galaxies aren't just moving apart. They're moving apart faster and faster. Something is pushing the universe outward. We call it dark energy, and it makes up about 68% of the total energy content of the universe. Dark matter is 27%. Normal matter, everything we've ever seen, touched, or studied, is less than 5%. We are the minority in our own universe. What is dark energy? Nobody knows. The simplest explanation is that it's the energy of empty space itself. Quantum mechanics predicts that even in a perfect vacuum, particles and antiparticles are constantly popping in and out of existence, borrowing energy from the vacuum and then annihilating back into nothingness. This quantum foam, as it's called, has energy. And energy, according to Einstein, is equivalent to mass. The energy of the vacuum could be what's driving the accelerated expansion. But there's a problem. When physicists calculate how much vacuum energy there should be, they get a number that's 10 to the power of 120 times larger than what we observe. That's a 1 followed by 120 zeros. It's the worst prediction in the history of physics. Something is wrong with our understanding. Either quantum mechanics is incomplete or general relativity is incomplete, or both. Some theories suggest that dark energy isn't constant. Maybe it changes over time, growing stronger or weaker as the universe ages. Maybe it's a new field, like an energy field permeating space called quintessence. Maybe it's a sign that we need to modify Einstein's equations, adding new terms that account for the behavior of space on cosmic scales. Or maybe dark energy is evidence of extra dimensions. In some versions of string theory, our universe is a three-dimensional membrane floating in a higher dimensional space. The gravitational influence of other branes, other universes, could appear to us as dark energy, an invisible force pushing our universe outward. The truth is, we're groping in the dark. We've discovered that 95% of the universe is made of stuff we don't understand, and that's both humbling and exhilarating. It means there's so much more to learn, so many mysteries waiting to be solved. Now let's talk about black holes. Not just what they are, but what they reveal about the nature of reality. A black hole is what you get when you compress matter so densely that space-time itself breaks. Take the sun and compress it down to a sphere about 6 kilometers across, and you've got a black hole. The escape velocity, the speed you'd need to break free from the surface, exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. Not matter, not energy, not information. The black hole is a one-way trip. At the center of a black hole is the singularity, a point of infinite density where our equations break down and physics as we know it ceases to function. General relativity predicts that all the matter falling into a black hole gets compressed to this single point, a place where the curvature of spacetime becomes infinite. But infinity is a red flag in physics. When your equations give you infinity, it usually means you're missing something, that your theory is incomplete. Quantum mechanics might provide the answer. In the realm of the very small, quantum effects become important. Near the singularity, space and time themselves might become grainy, pixelated, quantized into tiny units called Planck lengths and Planck times. At this scale, the singularity might not be a point but a tiny region where quantum gravity takes over. We don't have a complete theory of quantum gravity yet, but when we do, it might reveal what really happens at the center of a black hole. But here's the kicker. From the outside, you'd never know. If you watch someone fall into a black hole, you'd see them slow down as they approach the event horizon. Time dilation, caused by the intense gravity, makes their clock run slower and slower relative to yours. They'd appear to freeze at the horizon, their image redshifted and dimmed, fading away over infinite time. You'd never see them cross the event horizon. To you, they'd be stuck there forever. But from their perspective, nothing special happens at the horizon. They'd cross it in finite time, not even noticing the moment they passed the point of no return. They'd continue falling toward the singularity, and depending on the size of the black hole, they might have seconds or hours before they're torn apart by tidal forces. The difference in gravitational pull between their head and feet would become so extreme that they'd be stretched into a long, thin strand, a process affectionately called spaghettification. Black holes are cosmic laboratories where the laws of physics are pushed to their limits. They're also the ultimate information paradox. We've already talked about how information falling into a black hole might be encoded on the event horizon. But there's more. If black holes evaporate through Hawking radiation, then over time they shrink. Eventually, they disappear entirely. What happens to the information then? Some physicists think the information escapes in the Hawking radiation, encoded in subtle correlations between the particles emitted. Others think it's stored in a remnant, a tiny stable object left behind after the black hole evaporates. Still others think the information might tunnel out through a wormhole, emerging in another part of the universe or even another universe entirely. We don't know. The information paradox remains one of the deepest unsolved problems in theoretical physics. And speaking of wormholes, let's go there. Einstein's equations allow for shortcuts through spacetime, tunnels connecting distant regions of the universe. Travel through a wormhole, and you could cross billions of light years in an instant, arriving at your destination faster than light could travel through normal space. You wouldn't be breaking the speed of light. You'd be taking a shortcut, a path through a higher dimension that bypasses the long route through ordinary space. But there's a catch. Every solution that allows for traversable wormholes requires something called exotic matter. This isn't antimatter. It's matter with negative energy density, something that pushes outward instead of pulling inward. We've never seen exotic matter. We've never created it in a lab. Quantum mechanics hints that it might exist in tiny amounts, in the fleeting vacuum fluctuations of empty space, but whether you could gather enough to hold a wormhole open is an open question. Even if you could create a wormhole, stabilizing it would be a monumental challenge. The slightest disturbance, a single photon passing through, might cause the wormhole to collapse, sealing shut before you could traverse it. And if you did manage to keep it open, you'd have to worry about paradoxes. Wormholes could potentially allow for time travel, connecting not just different places but different times. You could enter one end and emerge from the other in the past. But time travel creates paradoxes. What if you traveled back and prevented your own birth? What if you killed your grandfather before he met your grandmother? Physicists have proposed several solutions to the time travel paradox. One is the Novikov self-consistency principle, which states that you can travel to the past, but you can't change it. Any action you take in the past was always part of history. You can't kill your grandfather because you didn't. The timeline is self-consistent, closed, immutable. Another solution is the many worlds interpretation. When you travel back and change the past, you don't change your own timeline. You create a new branch, a parallel universe where the changes occur. In that universe, you were never born, but in your original universe, everything remains the same. Time travel might be impossible, or it might be possible but self-limiting, with the laws of physics conspiring to prevent paradoxes. Or it might be possible and we're just not clever enough yet to figure out how. The universe is under no obligation to make sense to us. Let's talk about the Big Bang. Not what happened during it, but what happened before it. The Big Bang theory states that the universe began about 13.8 billion years ago in an extremely hot, dense state and has been expanding ever since. But what caused the Big Bang? What existed before it? For a long time, the answer was simple: nothing. Time itself began with the Big Bang. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because there is no before. But that answer has always felt unsatisfying, and physicists have been searching for alternatives. One idea is that the Big Bang emerged from a quantum fluctuation. In quantum mechanics, particles can spontaneously appear from nothing, borrowing energy from the vacuum and then disappearing. What if the entire universe is a quantum fluctuation? A region of space-time that tunneled into existence out of nothing, driven by the same quantum processes that create particle-antiparticle pairs. The universe wouldn't need a cause. It would be a natural, if improbable, consequence of quantum mechanics. Another idea is the cyclic model, which we touched on earlier. The universe undergoes endless cycles of expansion and contraction. Each Big Bang is followed by trillions of years of expansion, then a reversal, a big crunch where everything collapses back down, and then another Big Bang. In this model, the universe is eternal, with no beginning and no end, just an infinite sequence of cosmic cycles. Then there's the ekpyrotic model inspired by string theory. Our universe is a three-dimensional brain floating in higher dimensional space. Occasionally, our brain collides with another brain, and the energy of that collision manifests as a Big Bang. The universe isn't born from nothing. It's born from the collision of higher dimensional objects. We don't know which, if any, of these models is correct. We might never know. The evidence from before the Big Bang is erased by the Big Bang itself. The intense heat and density of the early universe scrambled the information, leaving us with only indirect clues. We can study the cosmic microwave background, the afterglow of the Big Bang, looking for patterns that might reveal the initial conditions. We can search for gravitational waves from the Big Bang, ripples in space-time that have been propagating through the universe since the beginning. But the ultimate origin, the true cause of the Big Bang, might be forever out of reach. Now let's dive into the really speculative stuff. Let's talk about the simulation hypothesis. The idea that we might be living inside a computer simulation. This isn't New Age mysticism. It's a serious philosophical and scientific question, and it's based on some compelling logic. Here's the argument. If civilizations continue to advance, they'll eventually develop the technology to create highly detailed simulations of reality, virtual worlds populated by conscious beings who don't know they're in a simulation. These simulated beings would have experiences, memories, emotions, all generated by computer code. If creating such simulations becomes possible, then any sufficiently advanced civilization would likely create many of them, perhaps millions or billions, for entertainment, research, or education. Now, if there are millions of simulated realities and only one base reality, then statistically, you're more likely to be in a simulation than in the real world. The odds favor you being a simulated consciousness inside someone else's computer rather than a biological being in the base layer of reality. But how would you know? If the simulation is perfect, if it obeys consistent laws of physics, if it includes all the details down to the quantum level, then there'd be no way to tell from the inside. You could search for glitches, anomalies, places where the simulation breaks down, but a sufficiently advanced simulation would be indistinguishable from reality. Some physicists have proposed ways to test the simulation hypothesis. One idea is to look for a maximum resolution in the universe, a pixel size below which nothing exists. In a computer simulation, there's always a smallest unit of computation. If we discover that spacetime is quantized, that there's a minimum length scale like the Planck length, it could be evidence that we're living in a simulation running on a computational grid. Another approach is to look for efficiency hacks in the code. A simulation doesn't need to render everything all the time. In a video game, distant objects are rendered in low detail until you get close. Maybe the universe works the same way. Maybe quantum mechanics, with its probabilistic nature and observer-dependent outcomes, is just an efficiency algorithm, computing reality only when observed. Before you measure a particle's position, it doesn't have one. The simulation doesn't waste resources calculating something no one is observing. This sounds crazy, but it's internally consistent. And the fact that we can even formulate the question tells you how far we've come in understanding the nature of reality. We're at a point where physicists seriously debate whether the universe is a hologram, a quantum computer, or a simulation. But let's be clear, the simulation hypothesis is unfalsifiable. If we find evidence of simulation, we might be right. But if we don't find evidence, it doesn't mean we're wrong. The simulation could be too good to detect. And that's the problem. Science requires testable predictions. If a theory can't be tested, it's not science. It's philosophy. Still, it's fun to think about. And who knows? Maybe in a few centuries, we'll be running our own simulations, creating virtual worlds so detailed that the beings inside them start asking the same questions we're asking now. Let's move on to another mind-bending concept. The universe might have more dimensions than the 3 of space and 1 of time that we experience. String theory, one of the leading candidates for a theory of everything, requires extra dimensions to be mathematically consistent. In some versions, there are 10 or 11 dimensions, most of them curled up so small that we can't perceive them. Imagine a garden hose. From far away, it looks one-dimensional, just a line. But zoom in and you see it's actually two-dimensional. There's length along the hose and a circular dimension around it. Extra dimensions could be like that. They exist, but they're compactified, rolled up into tiny loops at every point in space, too small to see or measure directly. These extra dimensions could explain a lot. They could explain why gravity is so much weaker than the other forces. Maybe gravity leaks into the extra dimensions, diluting its strength in our three-dimensional slice of reality. They could explain the hierarchy problem, the puzzle of why the Higgs boson has the mass it does. They could even explain dark matter and dark energy as manifestations of physics in the higher dimensions. Some theories suggest that our universe is a three-dimensional surface embedded in a higher dimensional bulk. We're like ants crawling on a piece of paper, unaware that the paper itself exists in a three-dimensional room. Everything we experience, all the forces and particles, is confined to our brain except for gravity, which can propagate through the bulk. This could explain why we haven't detected extra dimensions. We're stuck on the surface, unable to leave, and the only hint of the higher dimensions is the way gravity behaves. There are experiments trying to detect extra dimensions. Particle colliders like the Large Hadron Collider smash particles together at incredibly high energies, looking for signs of extra-dimensional physics. If extra dimensions exist, high-energy collisions might produce particles that escape into those dimensions, disappearing from our detectors. We'd see missing energy, a sign that something left our three-dimensional space. So far, we haven't seen it, but the search continues. Extra dimensions also raise the possibility of higher-dimensional black holes. In a universe with more dimensions, the mathematics of black holes changes. They could form more easily at lower energies. Some theories suggest that the Large Hadron Collider could create microscopic black holes that evaporate instantly through Hawking radiation. Don't worry, these wouldn't be dangerous. They'd be so small and short-lived that they'd vanish before they could absorb anything. But their existence would be proof of extra dimensions. Now let's talk about consciousness. What is it? How does it arise? And why does it exist at all? These are some of the hardest questions in science, and they touch on the nature of reality itself. Consciousness is your subjective experience, the feeling of what it's like to be you. When you see the color red, there's something it's like to experience that color. When you feel pain, there's something it's like to feel that pain. Philosophers call this qualia, the subjective quality of experiences. And here's the problem. We don't know how physical processes in the brain give rise to subjective experience. We can map every neuron, trace every connection, understand the chemistry of neurotransmitters, and still not explain why there's something it's like to be conscious. This is called the hard problem of consciousness, and it's distinct from the easy problems. The easy problems are things like explaining how the brain processes information, how it integrates sensory inputs, how it controls behavior. These are hard in practice but easy in principle. We can imagine solving them through neuroscience and cognitive science. But the hard problem asks why any of this should feel like anything at all. Why isn't the brain just a biological computer processing information without any subjective experience? Some scientists think consciousness is an emergent property of complex systems. When you have enough neurons connected in the right way, consciousness emerges like wetness emerges from water molecules. Individual neurons aren't conscious, but the whole system is. Others think consciousness is fundamental, a basic feature of the universe like mass or charge. In this view, even simple systems might have a tiny amount of consciousness, and complex systems like brains just have more of it. This is called panpsychism, and while it sounds mystical, some physicists and philosophers take it seriously. There's also the question of whether artificial intelligence can be conscious. If we build a computer sophisticated enough to mimic all the functions of the human brain, will it be conscious? Will there be something it's like to be that computer? Or will it be a philosophical zombie, a system that behaves as if it's conscious but has no inner experience? We don't know. We can't even agree on how to test for consciousness. We infer that other humans are conscious because they're similar to us, but we can't prove it. For all you know, you're the only conscious being in the universe, and everyone else is an automaton. This is called solipsism, and it's unfalsifiable. But let's assume other people are conscious. Let's assume consciousness is real and not an illusion. What role does it play in the universe? Some interpretations of quantum mechanics suggest that consciousness is necessary for wave function collapse, the moment when quantum possibilities become definite outcomes. Without an observer, the wave function never collapses. Reality remains in superposition. This is a controversial idea, and most physicists don't buy it. But it raises the question of what counts as an observer. Does it have to be conscious? Or is any measuring device enough? Can a rock observe? The universe seems indifferent to consciousness. It existed for billions of years before conscious beings evolved. It will exist for trillions of years after we're gone. And yet, consciousness might be the only way the universe knows itself. Without conscious observers, without beings capable of understanding and appreciating the cosmos, does the universe even matter? A tree falling in an empty forest makes a sound wave. But is there a sound without someone to hear it? The universe creates stars and galaxies and planets, but without consciousness to experience it, it's just physics. We are the universe's way of experiencing itself. That might sound poetic, but it's also true. The atoms in your body were forged in the cores of dying stars. You're made of stardust. You're a way for the cosmos to know what it's like to be a collection of atoms arranged in a specific way. And that's extraordinary. Let's shift to something more concrete. Alien life. Is it out there? And if so, where is it? The universe contains billions of galaxies, each with billions of stars, many of them with planets. The numbers are staggering. In our galaxy alone, there are an estimated 100 billion stars, and recent surveys suggest that most of them have planets. Some of those planets are in the habitable zone, the region where liquid water can exist on the surface. Life as we know it requires liquid water. If even a tiny fraction of planets in the habitable zone develop life, the galaxy should be teeming with it. And yet, we've found nothing. No signals, no probes, no artifacts, no evidence that intelligent life exists anywhere but here. This is the Fermi paradox. Where is everybody? There are dozens of proposed solutions to the Fermi paradox. Maybe life is incredibly rare. Maybe the jump from simple microbes to complex multicellular organisms is a fluke that almost never happens. Maybe intelligence is rare. Maybe the evolution of language, tool use, and technology is so unlikely that we're the only species in the galaxy to achieve it. Maybe civilizations destroy themselves before they become advanced enough to colonize the galaxy. Nuclear war, climate change, artificial intelligence, bioweapons. The universe is full of ways for intelligent species to go extinct. Or maybe they're out there, but they're not interested in us. Maybe advanced civilizations have better things to do than send signals to primitive species on backwater planets. Maybe they're hiding, deliberately avoiding contact to let us develop on our own. This is the zoo hypothesis. We're in a cosmic nature preserve, observed but not contacted. Or maybe they're so advanced that we wouldn't recognize them as life. They could exist as pure energy, as digital consciousnesses uploaded into vast computational networks, as beings that manipulate space-time itself. We're looking for radio signals and laser pulses, but maybe the evidence is all around us and we just don't know what we're looking for. There's also the possibility that we're first. The universe is 13.8 billion years old, but for the first few billion years, it was too hot and chaotic for planets to form. Stars had to live and die multiple times to produce the heavy elements necessary for planets and life. Maybe we're among the first intelligent species to emerge. The galaxy isn't silent because we're alone. It's silent because we're early. Or maybe the Great Filter is ahead of us. The Great Filter is the idea that there's some barrier, some challenge that prevents civilizations from spreading across the galaxy. Maybe it's behind us. Maybe the jump from non-life to life is the filter, and we've already passed it. Or maybe it's ahead of us. Maybe every civilization reaches a point where it develops technology capable of destroying itself, and very few survive that stage. If that's true, then our survival is not guaranteed. We might be approaching our own great filter right now. Despite the silence, we keep searching. The search for extraterrestrial intelligence, SETI, has been scanning the skies for decades, looking for signals from distant civilizations. So far, nothing. But the search has only just begun. We've searched a tiny fraction of the stars in our galaxy, and we've only looked at a narrow range of frequencies. Finding a signal is like finding a needle in a cosmic haystack. But if we do find one, it would change everything. It would tell us that we're not alone, that intelligence is not unique to Earth, that the universe is full of minds trying to understand their place in the cosmos, just like us. And even if we never find intelligent life, we might find simple life. Microbes on Mars, ice moons in the outer solar system, exoplanets with biosignatures in their atmospheres. Finding even a single microbe on another world would be one of the greatest discoveries in human history. It would tell us that life is common, that the universe is fertile, that wherever conditions allow, life takes root. And if life is common, then intelligence might be common too. We might not be alone. We might just be early. Let's talk about the end of the universe. Everything has an ending, even the cosmos itself. The universe is expanding, and it's expanding faster and faster, driven by dark energy. If this continues, and there's no reason to think it won't, then eventually galaxies will move so far apart that they'll no longer be visible to each other. The night sky will go dark, one star at a time, as distant galaxies recede beyond the cosmic horizon. This is called the Big Rip. In the most extreme versions, dark energy grows stronger over time, eventually overpowering not just gravity but all the forces. Galaxies are torn apart, then stars, then planets, then atoms. The universe ends in a crescendo of destruction, ripping matter itself into fundamental particles and then into nothing. But that's only one scenario. Another is the Big Freeze, also called heat death. In this scenario, the universe continues expanding, but dark energy remains constant. Stars burn out one by one over trillions of years. New stars stop forming as galaxies run out of gas. Black holes evaporate through Hawking radiation, taking quadrillions of years to disappear. Eventually, the universe becomes a cold, dark, empty expanse, with only a few lonely photons and fundamental particles drifting through infinite space. Entropy reaches its maximum. Nothing changes. Nothing can change. The universe reaches a state of equilibrium and stays there forever. There's also the Big Crunch. If there's enough matter in the universe, if dark energy weakens or reverses, then gravity could eventually halt the expansion and pull everything back together. The universe would collapse, galaxies merging, temperatures rising, until everything crunches back into a singularity. The Big Crunch could be the end, or it could be the beginning of a new cycle, a new Big Bang. And then there's vacuum decay. This one is terrifying. Our universe might not be in its most stable state. The Higgs field, the field that gives particles their mass, might be in a false vacuum, a temporary low-energy state. If it transitions to the true vacuum, a lower energy state, it would release a catastrophic amount of energy. A bubble of true vacuum would form somewhere in the universe and expand outward at the speed of light, obliterating everything in its path. The laws of physics inside the bubble would be different. Atoms would fall apart. Stars would cease to exist. There'd be no warning. One moment you're alive and the next you're not. The bubble wall passes through and you're gone. The good news is that even if vacuum decay is possible, it's probably incredibly rare. The universe has been around for nearly 14 billion years, and it hasn't happened yet. The odds are good that it won't happen for trillions or quadrillions of years, long after our sun has died and the Earth is a cold, lifeless rock. But the possibility is there, a reminder that the universe is not stable, that the ground we stand on, the very fabric of reality, could shift at any moment. But maybe the end isn't the end. Maybe the universe is just one phase in a larger cycle. Maybe new universes bubble up from quantum foam, each with its own laws of physics, its own dimensions, its own history. Maybe we're part of an eternal multiverse, where universes are born, live, and die, but the multiverse itself never ends. Maybe death and rebirth are built into the structure of existence. We don't know. We can make predictions based on our current understanding of physics, but physics is incomplete. We don't know what dark energy is. We don't know if vacuum decay is possible. We don't know what happens at the singularity of a black hole. Every answer we find raises new questions, and those questions might change everything we think we know about the fate of the cosmos. Now let's bring it back to something personal. What does all this mean for you, for your life, for your place in the universe? When you think about the scale of the cosmos, it's easy to feel insignificant. We live on a tiny planet orbiting an ordinary star in an average galaxy in an observable universe containing 2 trillion galaxies. You're one of 8 billion people on this planet, and humans have only existed for a blink of cosmic time. In a few billion years, the sun will expand into a red giant and swallow the Earth. In a few trillion years, all the stars will burn out. In the grand scheme of things, nothing we do matters. Right? Wrong. The universe doesn't care about you. It doesn't care about anything. It's not conscious. It doesn't have preferences or goals. But you do. You're a conscious being capable of experiencing beauty, love, curiosity, wonder. You're the universe experiencing itself, a localized pattern of complexity that can ask questions and seek answers. And that's rare. As far as we know, consciousness is vanishingly rare in the cosmos. Most of the universe is empty space. Most of the matter is lifeless. But here, on this tiny blue dot, life has emerged. Consciousness has emerged. And with it, meaning. Meaning isn't something you find in the universe. It's something you create. You decide what matters to you. You choose your values, your goals, your relationships. The fact that the universe is indifferent doesn't make your life meaningless. It makes it more precious. You have a brief window of existence, a few decades to explore, learn, create, connect. That's not insignificant. That's miraculous. And who knows? Maybe the universe needs us. Maybe consciousness plays a role we don't understand yet. Maybe observers are necessary for reality to exist, for quantum wave functions to collapse, for the multiverse to take shape. Maybe we're part of something larger, a cosmic process unfolding over billions of years. Or maybe we're just an accident, a random fluctuation in an indifferent cosmos. Either way, we're here. We exist. And that's enough. Let's talk about one more thing before we wrap up. The concept of cosmic pessimism versus cosmic optimism. Are we doomed? Or is the future bright? It depends on how you look at it. Cosmic pessimism says that the universe is hostile to life. Entropy increases, stars burn out, civilizations collapse. Intelligence might be a curse, a brief flicker of awareness in an uncaring void. We're born, we suffer, we die, and the universe moves on without us. Everything we build will crumble. Everything we love will end. There's no escape from the second law of thermodynamics. Decay is inevitable. But cosmic optimism says that while the universe is indifferent, it's also full of possibility. We're not doomed. We're just beginning. We've only been exploring the cosmos for a few decades. We've barely left our own planet. Who knows what we'll discover in the next century, the next millennium, the next million years. We might find ways to harness energy from black holes, to travel between stars, to upload our consciousness into machines and live indefinitely. We might solve the mysteries of dark matter and dark energy. We might contact alien civilizations and learn we're part of a galactic community. We might even find ways to escape the heat death of the universe, to tunnel into new universes or to create our own. The universe is vast and strange, and we've only scratched the surface. Every question we answer opens up new realms of inquiry. Every discovery reveals deeper mysteries. Science is not about finding final answers. It's about expanding the frontier of the known, pushing back the darkness, inch by inch, generation by generation. And as long as there are conscious minds asking questions, the pursuit of knowledge will continue. So here's where we stand. We live in a universe that's mostly empty space, filled with dark matter and dark energy we don't understand. We exist on a small planet orbiting a medium-sized star in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies, possibly in a multiverse of infinite universes. Time might be an illusion. Space might be a hologram. We might be living in a simulation. Consciousness might be fundamental to reality, or it might be an emergent property of complex computation. We don't know, and that's okay. The universe doesn't give us easy answers. It gives us challenges, puzzles, mysteries that take centuries to solve. And every time we solve one, we find 10 more waiting behind it. That's the beauty of science. It's an endless journey, a quest that never ends because there's always more to learn. And as long as there are people willing to ask questions, to look up at the stars and wonder what's out there, the journey will continue. So the next time you look up at the night sky, remember this. Those stars are not just distant balls of gas. They're forges where the elements of your body were created. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was cooked in the cores of stars that died billions of years ago. You're not separate from the universe. You're part of it. You're stardust that became conscious, a way for the cosmos to know itself. And maybe, just maybe, that's enough. Maybe the meaning of life isn't something written in the fabric of space-time. Maybe it's something we create ourselves, moment by moment, as we explore, discover, and share what we find. Maybe the universe doesn't need a purpose. Maybe we're the purpose. We're the ones who look up, who wonder, who ask why. And in doing that, we give meaning to an otherwise meaningless cosmos. That's the real cosmic theory. Not multiverse, not simulation, not holographic principle. The real theory is this: consciousness, awareness, curiosity. These are the universe's way of making sense of itself. We are the sense makers, and that's not insignificant. That's extraordinary. That's worth celebrating. So go ahead, look up at the stars, ask questions, seek answers, wonder, because in doing so, you're participating in the grandest adventure of all. The adventure of understanding, the adventure of existence, the adventure of being part of something infinitely larger than yourself, and yet intimately connected to every atom, every star, every galaxy, every universe that has ever existed or ever will. Welcome to the cosmos. You're home, but let's not stop there. There's so much more to explore, so many more theories that will bend your mind and reshape how you think about existence itself. Let's dive deeper into the quantum realm, into the strange world where particles can be in two places at once, where cause and effect blur together, where the very act of observation changes reality. Quantum entanglement. Einstein called it spooky action at a distance, and he didn't mean it as a compliment. He thought it proved quantum mechanics was incomplete, that there had to be some hidden variables we weren't seeing. But he was wrong. Quantum entanglement is real, and it's one of the weirdest phenomena in all of physics. When two particles become entangled, they form a single quantum system. Measure one particle and you instantly know the state of the other, no matter how far apart they are. And I mean instantly, faster than light. The correlation between entangled particles doesn't travel through space. It just is. This doesn't mean you can use entanglement to send information faster than light. When you measure one particle, the result is random. You can't control what you get. And the person measuring the other particle also gets a random result. It's only when you compare notes afterward, traveling at normal speeds, that you discover the correlation. But the correlation itself is instantaneous, and it exists across any distance. You could entangle two particles, send one to Mars, and the moment you measure yours on Earth, the one on Mars would have a definite state correlated with yours. The universe doesn't care about distance when it comes to quantum connections. What does this mean? Some interpretations suggest that entangled particles are not really separate. They're parts of a single system, spread across space but still fundamentally connected. Space in the quantum realm might be an illusion. What we perceive as separate objects might be deeply interconnected at a level we can't observe directly. The universe might be one vast, entangled quantum system, with everything connected to everything else. This has practical implications. Quantum computers exploit entanglement to perform calculations impossible for classical computers. Quantum cryptography uses entanglement to create unbreakable codes. If someone tries to intercept an entangled quantum message, the act of observation breaks the entanglement, and you know someone's listening. Quantum technology is moving from theory to reality, and it's going to change everything from medicine to artificial intelligence to cybersecurity. Now let's talk about quantum tunneling. In the quantum world, particles don't need to climb over barriers. They can tunnel through them. Imagine throwing a ball at a wall. Classically, if you don't throw it hard enough, it bounces back. But in quantum mechanics, there's a small probability that the ball will appear on the other side of the wall without ever passing through it. Tunnels. This sounds impossible, but it happens all the time at the atomic scale. Electrons tunnel through barriers in computer chips. Protons tunnel through energy barriers in the sun, allowing nuclear fusion to occur at temperatures lower than classical physics would allow. Without quantum tunneling, the sun wouldn't shine, and we wouldn't exist. Tunneling is also how radioactive decay works. The nucleus of a radioactive atom is held together by the strong nuclear force, but sometimes a particle tunnels through the energy barrier and escapes. This is alpha decay. The particle doesn't have enough energy to escape classically, but quantum mechanics allows it to tunnel out, and when it does, the atom transforms into a different element. This is alchemy, not through magic but through quantum mechanics. Quantum tunneling might even play a role in the origin of the universe. Some cosmologists suggest that the Big Bang itself was a quantum tunneling event. The universe tunneled out of nothing, borrowing energy from the vacuum and expanding into existence. In this view, the universe is the ultimate free lunch, a quantum fluctuation that grew into everything we see. It didn't need a cause. It didn't need a creator. It just needed the laws of quantum mechanics, which might be the only eternal, unchanging things in existence. Let's talk about antimatter. For every particle, there's an antiparticle with the same mass but opposite charge. Electrons have positrons. Protons have antiprotons. When matter and antimatter meet, they annihilate, converting their mass entirely into energy according to Einstein's equation E equals mc squared. This is the most efficient energy conversion possible. Nuclear bombs convert less than 1% of mass into energy. Matter-antimatter annihilation converts 100%. Here's the mystery. The Big Bang should have created equal amounts of matter and antimatter. But when we look around, we see only matter. Where did the antimatter go? This is called the matter-antimatter asymmetry, and it's one of the greatest unsolved problems in physics. If matter and antimatter were created in equal amounts, they should have annihilated each other, leaving behind only energy. The universe should be filled with photons and nothing else. No atoms, no stars, no you. But we exist, which means there was an asymmetry. For every billion antimatter particles, there were 1,000,000,001 matter particles. When the annihilation happened, that one extra matter particle survived. Do this 1,000,000,000 times and you get enough matter to build a universe. But why was there that extra particle? We don't know. Some theories suggest that certain particles decay differently depending on whether they're matter or antimatter, creating a small bias. Others suggest that the antimatter is still out there, in distant regions of the universe we can't see, separated from our matter-filled region by voids. If antimatter galaxies exist, they'd look identical to matter galaxies. Light is its own antiparticle, so photons from an antimatter star look just like photons from a regular star. We've created antimatter in laboratories. Particle accelerators produce antiprotons and positrons, and we've even created antiatoms, antihydrogen, where a positron orbits an antiproton. We've held antimatter in magnetic traps, studied its properties, confirmed that it behaves exactly like ordinary matter except for the opposite charge. If you could build a spaceship out of antimatter, it would work just fine. But you couldn't land it on Earth. The moment the antimatter hull touched matter atmosphere, it would explode with the force of a nuclear bomb. Antimatter might be the key to interstellar travel. The energy density is unparalleled. A kilogram of matter and a kilogram of antimatter would produce more energy than the largest nuclear weapon ever detonated. If we could produce and store antimatter efficiently, we could build rockets capable of reaching a significant fraction of light speed. But we're nowhere close. Producing antimatter is incredibly expensive, and storing it is even harder. It has to be suspended in a vacuum using magnetic fields, never touching the walls of the container. One mistake, one power failure, and the entire container annihilates. Let's shift to something mind-bending. The arrow of time. Why does time flow forward? Why do we remember the past but not the future? The laws of physics are time-symmetric. If you filmed a video of particles colliding and played it backward, the physics would still work. There's nothing in the equations that says time has to move forward. And yet, time clearly does have a direction. Eggs break but don't unbreak. People age but don't get younger. The universe expands but doesn't contract, at least not yet. The answer lies in entropy. The second law of thermodynamics states that entropy, the The measure of disorder always increases in a closed system. When you break an egg, the ordered structure of the shell shatters into disordered fragments. The entropy increases. You can't unbreak the egg because that would require entropy to decrease, and the second law forbids it. Time's arrow is entropy's arrow. Time moves in the direction of increasing entropy. But this raises a question. Why was entropy so low at the Big Bang? The early universe was incredibly hot and dense, which sounds chaotic. But in gravitational systems, clumping is low entropy and spreading out is high entropy. The early universe was remarkably smooth, remarkably uniform. That's a low entropy state. As the universe expanded and cooled, matter began to clump under gravity, forming stars and galaxies. Entropy increased. It's still increasing now, and it will continue increasing until the heat death of the universe, when entropy reaches its maximum and nothing changes anymore. So time flows forward because the Big Bang started the universe in a low entropy state, and entropy has been increasing ever since. But why did the Big Bang start with low entropy? We don't know. It's one of the deepest mysteries in cosmology. Some theories suggest that the universe is part of an eternal cycle, and the Big Bang was a bounce from a previous contracting phase. Others suggest that quantum fluctuations naturally create low entropy pockets in a sea of high entropy, and we live in one of those pockets. Or maybe the answer requires physics beyond what we currently understand. Now let's talk about cosmic inflation in more detail. In the first fraction of a second after the Big Bang, the universe expanded exponentially, doubling in size many times over in an unimaginably short period. This solves several problems. It explains why the universe looks the same in all directions. Before inflation, the universe was small enough for different regions to interact and reach equilibrium. Then inflation stretched those regions far apart, but they retained their uniformity. It also explains why the universe is flat. Inflation stretched space so much that any curvature became negligible, like blowing up a balloon until its surface looks flat. But inflation also makes predictions. It predicts that quantum fluctuations during inflation would be stretched to cosmic scales, creating tiny variations in the density of matter. These variations should show up as patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. And they do. We've measured these patterns with incredible precision using satellites like WMAP and Planck, and they match the predictions of inflation almost perfectly. This is one of the great triumphs of modern cosmology. Inflation also predicts gravitational waves from the Big Bang, ripples in spacetime created by the violent expansion. These primordial gravitational waves should leave a specific pattern in the cosmic microwave background, a pattern we're searching for right now. If we find it, it would be smoking gun evidence for inflation, confirmation that the universe really did undergo this period of exponential expansion. We haven't found it yet, but the search continues. And inflation has another consequence. If it started, it might never stop. Not everywhere at once, but in pockets. Most regions of the inflating spacetime would continue inflating forever, creating bubble universes like ours only in rare regions where inflation ends. This is eternal inflation, and it leads directly to the multiverse. Our universe is one bubble in an infinite ocean of bubbles, each with potentially different physical laws, different constants of nature, different histories. We're part of an ever-expanding, ever-branching structure that might have no beginning and no end. Let's explore another layer of weirdness. The Heisenberg uncertainty principle. You cannot simultaneously know both the position and momentum of a particle with perfect precision. The more accurately you measure one, the less accurately you can know the other. This isn't a limitation of our technology. It's a fundamental property of quantum mechanics. Particles don't have definite positions and momenta at the same time. Before you measure, they exist in a fuzzy quantum state, a superposition of possibilities. The act of measurement forces the particle to choose, to collapse into a definite state, but only for the property you're measuring. The other property remains uncertain. This has profound implications. It means there's a fundamental limit to how much information you can extract from nature. It means prediction is impossible at the quantum level. You can calculate probabilities, but you can never predict exactly what will happen. And it means that reality is inherently indeterministic. God, as Einstein famously said, does not play dice with the universe. But quantum mechanics says God does play dice, and the dice are loaded in strange and subtle ways we're still trying to understand. The uncertainty principle also tells us that the vacuum isn't empty. Even in a perfect vacuum, devoid of all matter and radiation, there are quantum fluctuations. Virtual particles pop in and out of existence, borrowing energy from the vacuum for brief moments before annihilating back into nothing. These fluctuations have real effects. They cause the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience an attractive force because there are fewer virtual particles between the plates than outside them. They contribute to the Lamb shift, a tiny change in the energy levels of hydrogen atoms. And they might be the source of Hawking radiation, the mechanism by which black holes evaporate. Let's talk about the speed of light. 300 million meters per second. It's not just the speed of light. It's the speed of causality, the maximum speed at which information can travel through the universe. Nothing with mass can reach this speed. As you accelerate, your mass increases, and it takes more and more energy to go faster. To reach light speed, you'd need infinite energy, which is impossible. Only massless particles like photons can travel at light speed, and they must always travel at light speed. They can never slow down or speed up. From the photon's perspective, if it had one, time doesn't pass. A photon emitted from a distant star and absorbed by your eye experiences no time between emission and absorption. The journey is instantaneous. But here's the strange part. The speed of light is constant in all reference frames. No matter how fast you're moving, no matter in which direction, if you measure the speed of light, you always get the same value. This seems impossible. If you're on a train moving at half the speed of light and you shine a flashlight forward, you'd expect the light to move at 1.5 times the speed of light relative to someone standing still. But it doesn't. It moves at exactly the speed of light, the same as always. How? The answer is relativity. Space and time adjust themselves to keep the speed of light constant. Time slows down for the moving observer. Distances contract. What seems like a fixed meter stick to you is shorter for someone moving relative to you. What seems like a fixed second to you is longer for someone moving fast. Space and time are not absolute. They're relative, dependent on your reference frame, and they warp and bend to ensure that light always travels at the same speed. This leads to paradoxes that boggle the mind. The twin paradox. Two twins, one stays on Earth, the other travels to a distant star at near light speed and returns. When the traveling twin comes back, less time has passed for them than for the twin who stayed home. The traveling twin is younger. This isn't hypothetical. We've measured it with atomic clocks on airplanes. Fly a clock around the world, and when you land, it's slightly behind a clock that stayed on the ground. Time literally moves slower when you're in motion. Or consider the ladder paradox. You're carrying a ladder through a barn, running at relativistic speeds. The ladder is 20 feet long, the barn is only 10 feet long. But due to length contraction, the ladder appears shorter when it's moving. From the barn's perspective, the ladder fits inside with room to spare. But from the ladder's perspective, the barn is contracted, and there's no way the ladder fits. Both perspectives are correct. Relativity doesn't have a preferred reference frame. What you measure depends on how you're moving, and both measurements are equally valid. This is the reality of living in a relativistic universe. Common sense doesn't apply. The faster you move, the stranger things get. And if you could somehow reach the speed of light, which you can't, the universe would contract to zero length in front of you, and all of time would pass in an instant. You'd cross the entire universe without experiencing any time at all. Let's talk about warp drive. Not the science fiction kind, but the real physics kind. Miguel Alcubierre, a Mexican physicist, discovered a solution to Einstein's equations that allows for faster-than-light travel without breaking relativity. The idea is to create a bubble of space-time around your ship. Space in front of the bubble contracts, pulling you forward. Space behind the bubble expands, pushing you along. The ship itself isn't moving through space. Space is moving around the ship. Since it's space that's moving, not the ship, you can go faster than light without violating relativity. Light speed is the limit for objects moving through space, but there's no limit on how fast space itself can expand or contract. The Alcubierre drive is mathematically consistent with general relativity. But there's a catch, and it's a big one. To create the warp bubble, you need exotic matter, the same stuff you'd need to hold a wormhole open. Matter with negative energy density. We've never seen it. We've never made it. And the amount you'd need is staggering, equivalent to the mass energy of Jupiter at minimum. Even if exotic matter exists, gathering that much would be beyond any foreseeable technology. There are other problems too. Hawking radiation, particles created by the warping of spacetime, might build up at the edge of the bubble and destroy it. And if you're traveling faster than light, you might not be able to steer. You'd have no control over where you're going because any information about your destination would be trapped outside your warp bubble, unable to reach you. You might end up anywhere or nowhere. But the mere fact that warp drive is consistent with the laws of physics is extraordinary. It means that faster-than-light travel isn't forbidden. It's just really, really hard. Maybe impossibly hard. Or maybe in a few centuries, someone will figure out how to manipulate spacetime in ways we can't imagine today, and warp drive will become reality. Stranger things have happened in the history of physics. Now let's explore neutron stars. When a massive star runs out of fuel, it can no longer support itself against gravity. The core collapses and the outer layers explode in a supernova. What's left behind is a neutron star, a sphere about 20 kilometers across, containing more mass than the Sun. Neutron stars are so dense that a teaspoon of neutron star material would weigh 1 billion tons on Earth. They're held up not by thermal pressure but by degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same state. Neutron stars spin. Some of them spin hundreds of times per second, faster than a blender. They have magnetic fields trillions of times stronger than Earth's, and they emit beams of radiation from their magnetic poles. As the star spins, the beams sweep across space like a lighthouse, and if the beam points toward Earth, we see a pulse. These are pulsars, and they're some of the most precise clocks in the universe. Some pulsars are so regular that they rival atomic clocks in accuracy. We use them to test relativity, to search for gravitational waves, to navigate spacecraft. But neutron stars also push the limits of physics. At their cores, matter is compressed to densities so high that we're not sure what state it's in. It might be a soup of quarks, the fundamental particles that make up protons and neutrons. It might contain exotic particles that don't exist anywhere else in the universe. It might be a superfluid, a liquid with zero viscosity that flows without friction. We don't know. Studying neutron stars is like having a laboratory for extreme physics, a place where matter is pushed beyond anything we can achieve on Earth. Neutron stars also create gravitational waves when they collide. In 2017, astronomers detected gravitational waves from 2 neutron stars spiraling into each other and merging. It was the first time we'd seen a cosmic event with both gravitational waves and electromagnetic radiation. Telescopes across the world swung into action, capturing the light from the collision, watching as the neutron stars tore each other apart and formed a black hole. The collision also created heavy elements, gold and platinum and uranium, forged in the intense heat and pressure of the merger. The gold in your jewelry was probably created in a neutron star collision billions of years ago, then scattered across space, eventually ending up on Earth. Let's talk about gamma-ray bursts. These are the most energetic explosions in the universe, releasing more energy in a few seconds than the Sun will emit in its entire lifetime. They come from collapsing massive stars or from colliding neutron stars, and they produce beams of gamma rays, the most energetic form of light. If a gamma ray burst occurred in our galaxy and its beam pointed at Earth, it could strip away our ozone layer, exposing the surface to deadly ultraviolet radiation. It would be an extinction-level event. Fortunately, gamma ray bursts are rare, and the odds of one occurring close enough to harm us are low. But they're out there, happening in distant galaxies billions of light-years away. We see them as brief flashes of gamma rays, lasting seconds to minutes, and then they fade. Each burst is the death cry of a star, a final scream of energy before it collapses into a black hole. And the fact that we can detect them from across the universe tells you how powerful they are. Some gamma ray bursts are followed by what's called an afterglow, a longer-lasting emission of light at lower energies. Astronomers use this afterglow to pinpoint the location of the burst, to identify the host galaxy, to study the environment where the burst occurred. It's forensic astronomy, piecing together the details of an explosion from the light it leaves behind. Now let's venture into the realm of quantum field theory. In this framework, particles aren't fundamental. Fields are. The universe is filled with fields, one for each type of particle. There's an electron field, a photon field, a quark field, a Higgs field. Particles are excitations in these fields, like ripples on a pond. When you see an electron, you're seeing a localized ripple in the electron field. When you see a photon, you're seeing a ripple in the photon field. This is a radical shift in how we think about reality. There are no particles. There are only fields stretching across all of space, and what we call particles are just vibrations in those fields. It's like the universe is a vast cosmic harp, and every particle is a note being played. The reason all electrons are identical is that they're all vibrations of the same field. The reason photons can be created and destroyed is that ripples in the photon field can appear and disappear. Energy and momentum are conserved, but the number of particles isn't. In quantum field theory, particles are just a convenient fiction, a way of thinking about the excitations of underlying fields. Quantum field theory also predicts that the vacuum is seething with activity. Virtual particles pop in and out of existence constantly, borrowing energy from the vacuum and paying it back before the uncertainty principle notices. These fluctuations are real. They affect the properties of real particles. They cause the Lamb shift, a tiny difference in energy levels in hydrogen atoms. They cause the anomalous magnetic moment of the electron, a slight deviation from what classical physics would predict. We've measured these effects to extraordinary precision, and quantum field theory predicts them perfectly. It's the most accurate theory in all of science, tested to better than 1 part in a trillion. But quantum field theory has problems. Can't incorporate gravity. General relativity, our theory of gravity, describes gravity as the curvature of spacetime. Quantum field theory describes forces as exchanges of particles. These two frameworks don't play well together. When you try to combine them, you get infinities, nonsensical results that break the math. Physicists have developed techniques to handle some of these infinities, a process called renormalization, but it's a patch, not a solution. We need a deeper theory, a theory of quantum gravity, and we don't have one yet. String theory is one attempt to solve this problem. In string theory, particles aren't points. They're tiny vibrating strings, about 10 to the power of negative 35 meters long, a billion times smaller than an atom. Different vibrations of the string correspond to different particles. An electron is a string vibrating one way. A photon is a string vibrating another way. Gravity, the graviton, is a string vibrating in yet another way. String theory naturally incorporates gravity, unifying all the forces of nature into a single framework. But string theory has its own problems. It requires extra dimensions, as we discussed earlier. It has multiple versions, 5 different string theories, and no clear way to choose between them. And it makes predictions that are far beyond our ability to test. The energy scale where string theory becomes important is the Planck scale, about 10 to the power of 19 billion electron volts. The Large Hadron Collider reaches energies of about 10 trillion electron volts. We'd need an accelerator the size of the galaxy to test string theory directly. It's not happening anytime soon. Still, string theory has taught us a lot. It's led to insights about black holes, about the nature of space-time, about mathematical structures that might underlie reality. It's a work in progress, and maybe it's not the final theory. Maybe it's a stepping stone to something deeper. Or maybe it's the right theory, and we'll never be able to test it directly. That's the frustration and the fascination of theoretical physics. Sometimes the universe plays by rules we can describe mathematically but can never test experimentally. Let's talk about loop quantum gravity. This is an alternative approach to quantum gravity, one that doesn't require extra dimensions or strings. Loop quantum gravity starts with space-time itself and tries to quantize it, to break it into discrete chunks. In this theory, space isn't continuous. It's made of tiny loops, woven together into a fabric called a spin network. These loops are incredibly small at the Planck scale, and they form the fundamental structure of space. Time in loop quantum gravity is also quantized. It doesn't flow smoothly but ticks forward in discrete steps. The universe is like a cosmic computer, updating itself one Planck time at a time. This solves the singularity problem in black holes and the Big Bang. When you try to compress space-time to a point, quantum effects kick in and prevent the singularity from forming. Instead, space-time bounces, rebounding outward. The Big Bang wasn't a singularity. It was a big bounce from a previous contracting phase. Loop quantum gravity is elegant, but it has challenges too. It's hard to extract predictions from the theory. The math is complicated, and connecting the quantum structure of space-time to the macroscopic world we observe is not straightforward. We're working on it. Both string theory and loop quantum gravity are attempts to answer the same question. What is space-time really made of? And both might be wrong. The correct theory of quantum gravity might be something no one has thought of yet. Now let's explore the concept of cosmic voids. The universe isn't uniformly filled with galaxies. It's structured like a sponge, with dense clusters of galaxies connected by filaments, and between them, vast empty regions called voids. These voids are hundreds of millions of light-years across, and they contain almost no galaxies. They're not empty of space. They're just empty of matter. And they're expanding faster than regions filled with galaxies because there's less matter to slow them down. The cosmic web, as it's called, formed from tiny density fluctuations in the early universe. Regions that were slightly denser attracted more matter through gravity, growing into clusters and filaments. Regions that were slightly less dense lost matter to their denser neighbors, becoming voids. Over billions of years, this structure has evolved, with matter flowing along the filaments like rivers, accumulating in clusters where filaments intersect. Our galaxy, the Milky Way, is part of the Virgo supercluster, a massive structure containing tens of thousands of galaxies, and we're located near the edge of a void called the local void. Studying the cosmic web helps us understand dark matter and dark energy. The distribution of galaxies traces the distribution of dark matter, which we can't see directly. And the expansion rate of voids tells us about the strength of dark energy. The universe is a vast laboratory, and by mapping its structure, we learn about the forces shaping it. Let's return to the idea of cosmic inflation, but look at a specific prediction: primordial gravitational waves. During inflation, quantum fluctuations in the fabric of space-time itself were amplified to cosmic scales. These fluctuations are ripples in space, gravitational waves, and they should have left an imprint on the cosmic microwave background radiation. The pattern is called B-mode polarization, and detecting it would be direct evidence of inflation. In 2014, a team announced they'd found B-modes in the CMB, and the physics community erupted with excitement. But it turned out to be a false alarm. The signal was caused by dust in our galaxy, not primordial gravitational waves. The search continues. New experiments are being built, detectors with greater sensitivity, looking for that faint signal from the earliest moments of the universe. If we find it, it will confirm that inflation really happened, and it will open a window into physics at energy scales far beyond anything we can reach with particle accelerators. Now let's talk about quasars. These are the brightest objects in the universe, supermassive black holes at the centers of galaxies, accreting matter at incredible rates. As matter spirals into the black hole, it heats up to millions of degrees, emitting vast amounts of light. A single quasar can outshine an entire galaxy containing 100 billion stars. And yet, all that light comes from a region smaller than our solar system. Quasars were common in the early universe billions of years ago, when galaxies were younger and gas was more abundant. Today, they're rare. Most supermassive black holes have run out of fuel, sitting quietly at the centers of galaxies, occasionally flaring to life when a star wanders too close. But in the early universe, quasars blazed, beacons of energy that could be seen across billions of light years. Studying quasars tells us about the conditions in the young universe, about how galaxies formed and evolved, about the growth of supermassive black holes. Some quasars emit jets, narrow beams of particles traveling at nearly the speed of light, shooting out from the poles of the black hole. These jets can extend for millions of light years, far beyond the host galaxy, interacting with intergalactic gas and creating vast lobes of radio emission. We call these radio galaxies, and they're among the largest structures associated with individual objects in the universe. Let's explore the concept of Hawking radiation in more detail. Stephen Hawking's greatest contribution to physics was the realization that black holes aren't completely black. Near the event horizon, quantum fluctuations create virtual particle-antiparticle pairs. Normally, these pairs annihilate almost immediately, but near a black hole, one particle can fall into the black hole while the other escapes. From the outside, it looks like the black hole is emitting a particle. This is Hawking radiation. The energy for the escaping particle comes from the black hole's mass. Over time, the black hole loses mass and shrinks. For large black holes, like the ones formed from collapsing stars, this process takes longer than the current age of the universe. But for tiny black holes, primordial black holes that might have formed in the Big Bang, evaporation could happen much faster. A black hole the mass of a mountain would evaporate in about the age of the universe, ending its life in a burst of gamma rays. Hawking radiation is thermal, meaning it has a temperature. Larger black holes are colder. A solar mass black hole has a temperature of about 1/millionth of a degree above absolute zero. A supermassive black hole at the center of a galaxy is even colder. But as a black hole evaporates and shrinks, its temperature increases. In its final moments, a black hole becomes incredibly hot, radiating furiously before disappearing in a flash. This creates the information paradox we discussed earlier. If Hawking radiation is truly thermal, it carries no information about what fell into the black hole. The information is lost. But quantum mechanics says information can't be destroyed. So where does it go? The resolution might involve the holographic principle. The information is encoded on the event horizon and gradually released in subtle correlations in the Hawking radiation. Or it might involve quantum corrections to Hawking's calculation, modifications that preserve information. Or the answer might be something even stranger. Black holes are still teaching us about the universe. Now let's discuss the fine-tuning problem. The constants of nature, things like the strength of gravity, the charge of the electron, the mass of the Higgs boson, seem finely tuned for life. Change any of them by a small amount, and the universe becomes inhospitable. Make gravity slightly stronger, and stars burn out too quickly for life to evolve. Make it slightly weaker, and stars can't form at all. Adjust the strong nuclear force, and atomic nuclei become unstable. Tweak the cosmological constant, the energy of the vacuum, and the universe either collapses immediately or expands so fast that galaxies never form. This fine-tuning seems suspicious. Why are the constants just right for life? One explanation is the anthropic principle, which we touched on earlier. We observe these values because we couldn't exist in a universe with different values. If there's a multiverse with different constants in each bubble universe, Then, of course, we find ourselves in one of the rare bubbles where the constants allow for life. It's selection bias. We're here because the conditions allow us to be here. But not everyone is satisfied with this explanation. Some see fine-tuning as evidence of design, a universe created specifically to allow for life. Others think we're missing something fundamental, that the constants aren't arbitrary but are determined by some deeper principle we haven't discovered yet. Maybe there's an underlying symmetry, a unifying theory that predicts the exact values of the constants. We don't know. The fine-tuning problem remains one of the great mysteries of cosmology. Let's talk about gravitational lensing. Mass bends spacetime, and light follows the curvature of spacetime. When light from a distant galaxy passes near a massive object like a cluster of galaxies, the path of the light bends, and the galaxy appears distorted, stretched into arcs or even multiple images. This is gravitational lensing, and it's one of the most powerful tools in astronomy. By studying how light is bent, we can map the distribution of mass in the lensing object, including dark matter. We can weigh galaxy clusters, measure the distribution of dark matter within them, and test our theories of gravity on cosmic scales. Gravitational lensing has confirmed that dark matter exists and that it's distributed in halos around galaxies and clusters. It's also allowed us to discover some of the most distant galaxies in the universe, magnified by foreground clusters acting as cosmic telescopes. In extreme cases, gravitational lensing creates Einstein rings, perfect circles of light where a distant source, a lens, and Earth are perfectly aligned. These are rare but spectacular, showcasing the warping of spacetime in action. Every time we see an Einstein ring, we're seeing Einstein's theory of relativity confirmed in the most dramatic way possible. Now let's explore the idea of cosmic strings. Not to be confused with the strings in string theory, cosmic strings are hypothetical one-dimensional defects in spacetime, like cracks in a freezing lake. They might have formed in the early universe during phase transitions, moments when the universe cooled and symmetries were broken. Cosmic strings would be incredibly thin, narrower than an atom, but immensely dense, with the mass of a mountain per meter of length. And they'd stretch across the universe, possibly for billions of light years. Cosmic strings would warp spacetime around them, creating unique gravitational effects. They could lens light in distinctive ways, and they could generate gravitational waves as they vibrate and intersect. So far, we haven't found any evidence of cosmic strings, but the search continues. If they exist, they'd be fossils from the earliest moments of the universe, physical relics of the Big Bang that we could study directly. Let's talk about the Planck epoch, the first 10 to the power of -43 seconds after the Big Bang. This is the Planck time, the smallest meaningful unit of time, and during this period, the universe was so hot and dense that quantum effects dominated everything. Space-time itself was a seething foam of quantum fluctuations, constantly creating and destroying tiny wormholes and black holes. The four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. We don't have a theory that describes this epoch. General relativity and quantum mechanics both break down. We need quantum gravity, and we don't have it, but we can speculate. During the Planck epoch, the universe might have been a quantum superposition of all possible geometries. Spacetime itself might not have been well defined. Cause and effect might have been meaningless concepts. This is the realm of quantum cosmology, where the universe is treated as a quantum object, and its history is a sum over all possible histories, just like in quantum mechanics. It's mind-bending and speculative, but it's the frontier of theoretical physics. After the Planck epoch came the grand unification epoch, when three of the four forces were still unified. Then the electroweak epoch, when electromagnetism and the weak nuclear force were one. Each phase transition, each moment when a symmetry was broken, released energy and shaped the evolution of the universe. These transitions might have created cosmic strings, magnetic monopoles, or other exotic remnants that we're still searching for today. Let's discuss the fate of Earth. Our sun is about 4.6 billion years old, halfway through its life. In another 5 billion years, it will exhaust the hydrogen in its core and begin fusing helium. It will swell into a red giant, expanding to 100 times its current size. Mercury will be engulfed. Venus will be engulfed. And Earth might be too. If Earth survives, it will be a scorched, lifeless rock, its oceans boiled away, its atmosphere stripped by the solar wind. Eventually, the sun will shed its outer layers, forming a planetary nebula, and its core will collapse into a white dwarf, a dense ember slowly cooling over trillions of years. But humanity might not be around to witness this. We have 5 billion years, which sounds like a lot, but there are many existential risks before then. Climate change, nuclear war, asteroid impacts, supervolcanic eruptions, pandemics, artificial intelligence, nanotechnology. We're living in a critical period for our species. The decisions we make in the next few centuries will determine whether we survive to become a multiplanetary, then interstellar, then perhaps even intergalactic civilization, or whether we go extinct, just another failed experiment in the history of life on Earth. The good news is that we're aware of the risks. We're working on solutions. We're developing technologies to deflect asteroids, to combat climate change, to ensure that artificial intelligence remains beneficial. We're planning missions to Mars, to the moons of Jupiter and Saturn, laying the groundwork for a future where humanity is no longer confined to a single planet. If we can survive the next few centuries, our future is bright. We could spread across the solar system, then the galaxy, becoming a spacefaring civilization that endures for millions or billions of years. Let's explore terraforming, the idea of transforming other planets into Earth-like worlds. Mars is the most obvious candidate. It has a day length similar to Earth's, about 24.5 hours. It has water ice at the poles and possibly liquid water beneath the surface. And it has carbon dioxide in its atmosphere, which could be used to thicken the atmosphere and warm the planet through a greenhouse effect. Terraforming Mars would take centuries, possibly millennia. We'd need to release greenhouse gases to warm the planet, melt the ice caps, and create a thicker atmosphere. We'd need to introduce microbes to produce oxygen through photosynthesis, gradually making the atmosphere breathable. We'd need to protect the planet from solar radiation, perhaps by generating an artificial magnetic field. It's an enormous undertaking, but it's not impossible. And it might be necessary if we want to ensure the long-term survival of our species. Venus is another candidate, though more challenging. Venus is a hellish world with surface temperatures hot enough to melt lead and atmospheric pressure 90 times that of Earth. But high in the atmosphere, about 50 kilometers up, conditions are more hospitable. The temperature is about room temperature, and the pressure is similar to Earth's surface. We could build floating cities in the clouds of Venus, habitats suspended by buoyancy, harvesting carbon dioxide and sulfuric acid from the atmosphere for resources. Sounds like science fiction, but the physics checks out. Then there are the moons of the outer solar system.
Europa, Enceladus, Titan.
These worlds have subsurface oceans of liquid water, kept warm by tidal heating from their parent planets. Europa's ocean might contain twice as much water as all of Earth's oceans combined. If life exists in these oceans, it would be one of the greatest discoveries in history. And if it doesn't, we could seed them with life from Earth, creating new biospheres in the outer solar system. Now let's talk about Dyson spheres. Freeman Dyson proposed that an advanced civilization might eventually need more energy than its home planet provides. The solution: build a megastructure around the star, capturing all of its energy output. A Dyson sphere isn't a solid shell. That would be unstable and impractical. It's a swarm of solar collectors, millions or billions of independent satellites orbiting the star, each one harvesting energy and beaming it to where it's needed. A civilization that builds a Dyson sphere would have access to billions of times more energy than we currently use. They could power entire planets, run massive computational systems, even manipulate matter at the atomic level. And from the outside, a Dyson sphere would look strange. The star would be dimmed, most of its light absorbed by the collectors, with only waste heat radiated at infrared wavelengths. We're searching for Dyson spheres now, looking for stars with unusual infrared signatures, but so far we haven't found any. Either they're rare or advanced civilizations don't build them, or we're not looking in the right way. Let's explore the idea of von Neumann probes. These are self-replicating spacecraft, named after mathematician John von Neumann. A civilization sends out a probe to a distant star system. The probe arrives, finds resources, and builds copies of itself. Those copies head to other star systems and repeat the process. Exponential growth. Within a few million years, a single probe could explore an entire galaxy. If any civilization in our galaxy developed von Neumann probes, even just once in the last billion years, the galaxy should be filled with them by now. And yet, we don't see them. No probes have visited Earth. No artifacts have been found on the Moon or Mars. This is another version of the Fermi paradox. Where are the probes? Maybe self-replication is harder than we think. Maybe civilizations don't build probes because they're dangerous, capable of consuming entire star systems if the programming goes wrong. Or maybe the probes are here, and we just don't recognize them. They could be microscopic, operating on scales we can't detect. They could be hiding, observing but not interfering. Or they could have been and gone, millions of years before humans evolved, leaving no trace. Now let's discuss the Drake equation. This is an attempt to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. It multiplies together several factors: the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction that develop life, the fraction that develop intelligent life, the fraction that develop technology capable of communication, and the length of time such civilizations remain detectable. The problem is, we don't know most of these numbers. We have good estimates for the first few. Stars form at a predictable rate, and most stars have planets. But how often does life arise? How often does intelligence evolve? How long do civilizations last? These are complete unknowns. Plug in optimistic numbers, and the galaxy is teeming with civilizations. Plug in pessimistic numbers, and we're alone. The truth is probably somewhere in between, but we won't know until we either detect a signal or explore enough of the galaxy to be confident that we're alone. Let's explore the concept of panspermia. The idea that life didn't originate on Earth but was transported here from elsewhere. Maybe life began on Mars, when Mars was warmer and wetter, and was carried to Earth on meteorites blasted off the Martian surface by asteroid impacts. We know that rocks can travel from Mars to Earth. We've found Martian meteorites on Earth. And we know that some microbes can survive the harsh conditions of space, radiation, vacuum, extreme cold, for extended periods. It's plausible that life could survive the journey. Or maybe life's origins are even more exotic. Directed panspermia is the idea that life was deliberately seeded on Earth by an advanced civilization. They might have sent probes carrying microbes, spreading life across the galaxy like farmers planting seeds. This sounds far-fetched, but it's not impossible. If we ever become an advanced spacefaring civilization, we might do the same, sending life to barren worlds to give evolution a head start. Now let's talk about Boltzmann brains. This is one of the strangest ideas in cosmology. In a universe approaching heat death, where entropy is near its maximum, there are still quantum fluctuations. Occasionally, purely by chance, these fluctuations could assemble into complex structures. Most of the time, they create simple things, a few particles, a small region of low entropy. But very rarely, they could create something as complex as a brain, complete with memories and thoughts. This is a Boltzmann brain, a conscious observer that pops into existence out of random fluctuations, exists for a brief moment, and then dissipates back into chaos. Here's the disturbing part. If the universe lasts forever, approaching heat death but never quite reaching it, then an infinite amount of time passes. And in infinite time, even incredibly unlikely events happen infinitely many times. That means there will eventually be far more Boltzmann brains than biological brains like ours. Most conscious observers in the universe will be Boltzmann brains, not evolved organisms. And statistically, you should expect to be a typical observer, which means you should expect to be a Boltzmann brain. But if you're a Boltzmann brain, your memories are random, not reliable. Everything you think you know about the universe, your past, the world around you, could be a false memory created by a quantum fluctuation. This is deeply unsettling and probably wrong. Most physicists think the Boltzmann brain paradox points to a flaw in our understanding, either of thermodynamics, of cosmology, or of consciousness itself. But it's a reminder that when you take physics to its logical extremes, you encounter weirdness that challenges your basic assumptions about reality. Let's return to the concept of entropy and dive deeper. Entropy is often described as disorder, but that's not quite right. Entropy is the number of ways a system can be arranged while still looking the same at a macroscopic level. A deck of cards in perfect order, ace through king of each suit, has low entropy. There's only one arrangement that looks like that. But a shuffled deck has high entropy. There are countless arrangements that all look shuffled. Entropy increases because there are far more disordered states than ordered states, and random processes naturally move systems toward more probable configurations. But entropy has a deeper connection to information. In the 1940s, Claude Shannon developed information theory and discovered that the formula for information is identical to the formula for entropy. This isn't a coincidence. Entropy measures missing information, how much you don't know about the microscopic details of a system. A low-entropy system is predictable. A high-entropy system is unpredictable, full of hidden information. This connects entropy to black holes through the Bekenstein-Hawking formula, which says that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This was shocking. For normal objects, entropy scales with volume, the number of particles inside. But for black holes, it scales with surface area. This is one of the clues that led to the holographic principle. If the maximum entropy of a region of space is determined by its surface area, then maybe the information about the interior is encoded on the surface. The universe is a hologram. Now let's discuss the anthropic principle in more detail. There are two versions, weak and strong. The weak anthropic principle says that we observe the universe we do because we're here to observe it. It's a selection effect. The strong anthropic principle says that the universe must have properties that allow for conscious observers to exist at some point. This is more controversial. It suggests that the universe is somehow constrained to produce observers, that consciousness is a fundamental feature, not an accident. Some interpretations of quantum mechanics, like the participatory anthropic principle proposed by John Wheeler, suggest that observers are necessary to make the universe real. The act of observation collapses the wave function, turning quantum possibilities into definite outcomes. Without observers, the universe would remain in superposition, a ghost of probabilities. In this view, we're not just passive observers. We're participants in the creation of reality. The universe doesn't exist without us to observe it. This sounds mystical, but it's based on the mathematics of quantum mechanics. It's one interpretation among many, and not all physicists accept it. But it raises profound questions about the relationship between consciousness and reality, questions that we're nowhere close to answering. Let's talk about the cosmic microwave background in more depth. This is the afterglow of the Big Bang, photons that have been traveling through space for nearly 14 billion years. When the universe was about 380,000 years old, it cooled enough for electrons and protons to combine into hydrogen atoms. Before this, photons were constantly scattered by free electrons, and the universe was opaque. After recombination, photons could travel freely. The cosmic microwave background is a snapshot of the universe at that moment, the oldest light we can see. The CMB is remarkably uniform, with a temperature of about 2.7 Kelvin in all directions. But there are tiny variations, fluctuations at the level of 1 part in 100,000. These fluctuations are the seeds of all structure in the universe. Regions that were slightly denser attracted more matter through gravity, eventually forming galaxies and clusters. The pattern of fluctuations encodes information about the early universe, about the density of matter, the strength of dark energy, the rate of expansion. By studying the CMB, we've determined the age of the universe, its composition, and its geometry with extraordinary precision. The CMB also contains polarization, patterns in the orientation of the light waves. There are two types, E modes and B modes. E modes are caused by density fluctuations and have been detected. B modes can be caused by two things, gravitational lensing and primordial gravitational waves from inflation. We've detected B modes from lensing, but not yet from inflation. Finding inflationary B modes would be a monumental discovery, direct evidence of the inflationary epoch and a window into physics at energy scales far beyond anything we can reach on Earth. Let's explore the idea of baby universes. Some theories suggest that black holes might be portals to other universes. When matter falls into a black hole, it doesn't just disappear. It creates a new region of space-time, a baby universe budding off from our own. From the outside, we see a black hole. But from the inside, it's a new universe expanding and evolving on its own. If this is true, then our universe might be the interior of a black hole in a larger parent universe. And every black hole we see might contain an entire universe of its own, complete with galaxies, stars, and perhaps even life. This is speculative, but it's consistent with some versions of quantum gravity. It also suggests a kind of cosmic natural selection. Universes that produce many black holes create many baby universes, passing on their physical constants. Over time, the multiverse would be dominated by universes fine-tuned to produce black holes, which requires stars, which requires the right physical constants. This might explain why our universe has the properties it does, not because we're special, but because universes like ours are good at reproducing. Now let's discuss the concept of quantum immortality. This is a bizarre consequence of the many worlds interpretation. Every time you face a situation that could result in death, the universe splits. In some branches, you die. In others, you survive. From your subjective perspective, you only ever experience the branches where you survive. You can never experience your own death because there's no you to experience it. You're always on a timeline where you miraculously survive, no matter how improbable. This doesn't mean you're invincible. Other people can still observe your death. And in most branches, you do die. But from your perspective, you seem to live forever, experiencing increasingly unlikely events as you age. Most physicists don't take quantum immortality seriously. It's more of a thought experiment than a prediction. But it highlights the strange implications of the many worlds interpretation and the difficulty of thinking about consciousness in a branching multiverse. Let's talk about vacuum energy and the cosmological constant problem. The cosmological constant is a term in Einstein's equations that represents the energy of empty space. Einstein originally introduced it to make the universe static, balancing gravity. When he learned the universe was expanding, he called it his greatest blunder and removed it. But in the late 1990s, astronomers discovered that the expansion of the universe is accelerating, driven by dark energy, which behaves like a cosmological constant. Einstein's blunder turned out to be right. The problem is, when physicists calculate how much vacuum energy there should be based on quantum field theory, they get a number that's 10 to the power of 120 times larger than what we observe. This is the worst prediction in the history of physics, off by a factor so large it's almost incomprehensible. Something is canceling out most of the vacuum energy, but we don't know what. It's as if there are two huge numbers, one positive and one negative, that nearly but not perfectly cancel, leaving a tiny residual value that we observe as dark energy. Why? Nobody knows. Some theories suggest that the vacuum energy we observe is determined by the anthropic principle. In a multiverse with different vacuum energies in different regions, only those with small vacuum energy allow galaxies and stars to form. We observe a small value because we couldn't exist in a universe with a large value. Is selection bias again? But this explanation is unsatisfying to many physicists. It feels like giving up on finding a deeper cause. Now let's talk about cosmic rays. These are high-energy particles, mostly protons, that bombard Earth from space. They're created in supernova explosions by pulsars by active galactic nuclei, and we're still not entirely sure where the highest energy ones come from. Some cosmic rays have energies so high that they shouldn't exist according to our understanding of physics. They're called ultra-high-energy cosmic rays, and they're a mystery. When a cosmic ray hits Earth's atmosphere, it creates a shower of secondary particles, a cascade that can contain billions of particles by the time it reaches the ground. We detect these showers with arrays of detectors spread over vast areas, piecing together the energy and direction of the original cosmic ray. Studying cosmic rays tells us about the most violent processes in the universe, about particle acceleration in extreme environments, about magnetic fields in space. And maybe, just maybe, they'll reveal new physics, particles, or interactions we haven't discovered yet. Let's explore the concept of time crystals. These are strange states of matter that break time translation symmetry. Normal crystals break spatial symmetry. Their atoms are arranged in a repeating pattern in space. Time crystals break temporal symmetry. They have a structure that repeats in time, oscillating without any energy input. This sounds impossible. This perpetual motion, a system that keeps moving without using energy. But time crystals are real. They've been created in laboratories using chains of ions or arrays of qubits. They don't violate the laws of thermodynamics because they're in their ground state, their lowest energy configuration. They're not doing work. They're just oscillating, a quantum mechanical curiosity with potential applications in quantum computing. Now let's discuss the possibility of life based on different chemistry. All life on Earth is carbon-based, using water as a solvent. But silicon, which is chemically similar to carbon, could potentially form complex molecules. Silicon-based life might exist on worlds where carbon is scarce and silicon is abundant. It might use liquid methane or ammonia as a solvent instead of water. Titan, Saturn's largest moon, has lakes of liquid methane and a thick nitrogen atmosphere. It's cold, minus 180 degrees Celsius, but some scientists speculate that exotic life forms might exist there, using chemistry so different from ours that we might not recognize it as life. There could also be life based on entirely different principles. What if life doesn't need molecules at all? What if consciousness can exist as patterns in plasma, in magnetic fields, in the quantum states of neutron stars? We define life by what we know, but the universe might be more creative than we imagine. Life, in its broadest sense, might be any system that can maintain itself, reproduce, and evolve. By that definition, there could be forms of life we haven't even conceptualized yet, existing in environments we consider utterly inhospitable. Let's return to the concept of gravitational waves but explore their detection in more detail. Einstein predicted gravitational waves in 1916, but he thought they'd be too weak to ever detect. He was almost right. It took a century and the development of incredibly sensitive instruments to finally see them. The Laser Interferometer Gravitational Wave Observatory, LIGO, uses lasers to measure changes in distance smaller than the width of a proton. When a gravitational wave passes through, it stretches space in one direction and compresses it in another, causing tiny changes in the length of LIGO's arms. By detecting these changes, LIGO can hear the universe, listening to colliding black holes and neutron stars billions of light years away. Gravitational wave astronomy is a new window on the cosmos. Light tells us about electromagnetic processes, about stars and galaxies. But gravitational waves tell us about the most violent events, about black holes merging, about neutron stars colliding, about the Big Bang itself. Future detectors, like the space-based LISA mission, will be sensitive to lower-frequency gravitational waves, allowing us to detect supermassive black hole mergers and test general relativity in entirely new regimes. And who knows what else we'll discover when we can finally listen to the whispers of spacetime itself. Now let's talk about the possibility of traversable wormholes as time machines. If you could create a wormhole and move one end relative to the other at high speed, the two ends would age differently due to time dilation. Travel through the wormhole, and you'd emerge not just in a different place but at a different time. You'd have a time machine, but time machines create paradoxes, and physicists argue about whether the universe allows them. Stephen Hawking proposed the chronology protection conjecture, which states that the laws of physics prevent time machines from forming. Whenever you try to create closed time-like curves, quantum effects build up and destroy the time machine. Maybe the universe has a built-in safety mechanism that prevents paradoxes. Or maybe time travel is possible, but only in ways that don't create contradictions. Maybe the universe self-corrects, ensuring that timelines remain consistent. We don't know. Time machines remain theoretical, a playground for physicists to test the boundaries of general relativity and quantum mechanics. Let's discuss the concept of observer selection effects. When we make observations about the universe, we have to account for the fact that we're observers, and observers can only exist in certain types of universes. This biases our observations. For example, we might wonder why the universe is 13.8 billion years old. Why not younger or older? But younger universes haven't had time to form stars and planets and life. Older universes might have already suffered heat death, with no stars left to support life. We observe the universe at this particular age because observers like us can only exist in universes of roughly this age. It's a selection effect. This reasoning can be applied to many questions. Why is the cosmological constant so small? Why are the physical constants fine-tuned? Maybe they're not fine-tuned. Maybe there's a multiverse with all possible values, and we observe the values we do because we couldn't exist in universes with different values. Observer selection effects are a powerful tool, but they're also controversial. They can explain anything by appealing to the multiverse, which makes some physicists uncomfortable. If a theory can't be falsified, is it really science? Now let's explore the idea of cosmic censorship. This is a conjecture by Roger Penrose that nature abhors naked singularities. A singularity is a point of infinite density, like the center of a black hole. In general relativity, singularities are hidden behind event horizons, boundaries that prevent information from escaping. But what if you could create a singularity without an event horizon, a naked singularity? It would be a place where the laws of physics break down, visible to the outside universe, able to affect everything around it in unpredictable ways. Penrose conjectured that the universe forbids this, that whenever a singularity forms, it's always clothed by an event horizon. This is cosmic censorship, and it's been tested in many scenarios but never proven. It might be a fundamental principle, or it might be violated under extreme conditions we haven't explored yet. Let's talk about the multiverse typology. Physicist Max Tegmark proposed 4 levels of multiverse. Level 1 is the simplest. Space is infinite and beyond our observable universe. There are other regions, other Hubble volumes, forever out of reach. These regions are just like ours, governed by the same laws of physics, but with different initial conditions. Somewhere out there, infinitely far away, there's another you reading these words. Level 2 is the bubble universe multiverse from eternal inflation. Each bubble has its own physical constants, its own laws of physics, determined by how the field settled during the end of inflation. Level 3 is the many worlds interpretation of quantum mechanics, where every quantum measurement splits the universe into branches. And level 4 is the mathematical universe hypothesis, the idea that every mathematically consistent structure exists as a physical universe. If a mathematical structure is logically coherent, it's real, and we live in one such structure. Level 4 is the most radical. It suggests that the universe is mathematics, that physical existence and mathematical existence are the same thing. We're not discovering mathematics. We're discovering the structure of the universe itself, which happens to be mathematical. This is deeply philosophical and probably untestable, but it's a fascinating idea. Mathematics isn't just a tool we use to describe reality. It is reality. Now let's return to the practical. Space colonization. If humanity is to survive long-term, we need to become a multiplanetary species. Mars is the obvious first target, but it's not the only option. The moon is closer, with water ice at the poles that could be used for drinking water and rocket fuel. Asteroids contain vast amounts of metals and other resources, perfect for building space habitats. And the outer solar system offers strange new worlds, moons with subsurface oceans, frozen landscapes that might harbor life. Building a self-sustaining colony is incredibly difficult. You need life support systems that can recycle air and water indefinitely. You need agriculture, growing food in artificial environments. You need power, probably from solar panels or nuclear reactors. You need protection from radiation, either through thick shielding or underground habitats. And you need a way to get there, rockets capable of carrying large payloads and large numbers of people. We're working on all of this. SpaceX, Blue Origin, NASA, and other organizations are developing the technologies needed for space colonization. It might happen in our lifetimes or it might take centuries, but it's coming. And once we're established on Mars, the next step is the stars. Interstellar travel is far more challenging. The nearest star system, Alpha Centauri, is 4.3 light-years away. With current rockets, it would take tens of thousands of years to get there. We need faster propulsion. Nuclear pulse propulsion, using nuclear explosions to push a spacecraft, could reach a few percent of light speed. Laser sails, thin reflective sails pushed by powerful lasers from Earth, could reach similar speeds. Or antimatter rockets, if we can ever produce and store antimatter efficiently. Even at 10% of light speed, a journey to Alpha Centauri would take 40 years. Interstellar travel requires patience and commitment on timescales longer than human lifetimes. Generation ships, carrying thousands of people who live and die during the journey, might be necessary. Or we might send robots first, building infrastructure before humans arrive. Some theorists propose more exotic ideas. Sleeper ships, where passengers are cryogenically frozen for the journey. Or digital uploads, where consciousness is transferred to computers, allowing minds to travel at the speed of light as radio signals, reconstructed at the destination. These are speculative, but they're within the bounds of physics. If we survive long enough, we'll figure out how to reach the stars. Let's talk about the search for technosignatures. Instead of searching for radio signals, we're looking for signs of advanced technology. Industrial pollution in the atmospheres of exoplanets. Heat signatures from Dyson spheres. Laser beams used for communication or propulsion. Artificial structures orbiting stars. If an advanced civilization exists, they're probably not hiding. They're engineering their environment, building megastructures using vast amounts of energy. We should be able to detect these signs if we look carefully enough. Projects like Breakthrough Listen are scanning millions of stars, looking for any sign of artificial signals. So far, nothing definitive. But the search has only just begun. The universe is vast, and we've barely scratched the surface. If intelligent life is out there, we'll find it eventually. Or they'll find us. Now let's discuss the concept of the Great Attractor. Galaxies in our region of space are moving toward a gravitational anomaly about 200 million light-years away. It's called the Great Attractor, and it's pulling our galaxy and thousands of others toward it at hundreds of kilometers per second. For a long time, we couldn't see it directly because it's hidden behind the plane of the Milky Way, obscured by dust and stars. But using X-rays and other wavelengths, we've mapped the region and discovered a massive concentration of galaxies, the Norma cluster and the Shapley concentration beyond it. The Great Attractor isn't a single object. It's a region of space with unusually high mass density, pulling everything around it inward. And beyond the Great Attractor, there's an even larger structure pulling on us, the Shapley supercluster, containing tens of thousands of galaxies. We're falling toward it, and there's nothing we can do to stop it. The universe's large-scale structure is constantly in motion, galaxies flowing along rivers of dark matter, clustering and merging over billions of years. Let's explore the anthropic reasoning in cosmology more. Some physicists argue that the universe's initial conditions were incredibly fine-tuned. If the density of matter had been slightly higher, the universe would have collapsed in a big crunch. If it had been slightly lower, galaxies wouldn't have formed. The initial conditions were balanced to about 1 part in 10 to the power of 60. That's not just fine-tuning, that's engineering-level precision. How do we explain it? Inflation provides part of the answer. It flattens the universe, driving the density toward the critical value. But inflation requires its own fine-tuning. The inflaton field, the field that drives inflation, needs to start in just the right state. So you've replaced one fine-tuning problem with another. The multiverse offers an explanation. If there are countless universes with different initial conditions, then of course we find ourselves in one of the rare universes where the conditions are right for life. But this feels like giving up on finding a deeper explanation. Maybe there's a deeper principle, a reason why the universe must be this way, that we haven't discovered yet. Now let's talk about neutronium. This is the material that makes up neutron stars, matter compressed so densely that protons and electrons merge into neutrons. It's the densest stable matter in the universe. A teaspoon would weigh billions of tons. But neutronium only exists under the extreme pressure inside a neutron star. If you somehow extracted a piece and brought it to Earth, it would explode violently, the neutrons decaying into protons and electrons, releasing enormous amounts of energy. Neutronium is stable only when crushed by gravity. Remove the pressure and it disintegrates. Some science fiction imagines using neutronium as a material for construction, building indestructible structures or weapons. But it's not practical. The moment you try to use it, it turns back into normal matter with catastrophic results. Neutronium exists only in the cores of dead stars, a reminder that some things in the universe are too extreme for us to harness. Let's discuss the Unruh effect. If you accelerate in empty space, you'll observe a thermal bath of particles, even though someone in an inertial frame sees only vacuum. Acceleration creates particles from the quantum vacuum, a phenomenon related to Hawking radiation. The Unruh effect is tiny. You'd need to accelerate at trillions of meters per second squared to observe a temperature of even a single Kelvin. But it's real, and it's been confirmed indirectly through related phenomena. It tells us that the concepts of particles and vacuum are observer-dependent. What you see depends on how you're moving. There's no absolute notion of empty space. It's relative, like so many things in physics. Now let's explore the concept of the observable universe versus the entire universe. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It's about 93 billion light-years in diameter, larger than you'd expect from the age of the universe because space itself has been expanding. But the entire universe might be much larger, possibly infinite. We can never see beyond the observable universe because light from those regions hasn't reached us yet. And as the universe expands, regions that are currently observable will eventually move beyond our horizon, receding faster than light due to the expansion of space. Billions of years from now, distant galaxies will fade from view, and the night sky will darken. Eventually, only our local group of gravitationally bound galaxies will remain visible. The universe will seem smaller, lonelier, as the rest of the cosmos slips away forever. Let's talk about the mystery of the missing antimatter in more detail. In the early universe, there should have been equal amounts of matter and antimatter. But when we look around today, we see almost no antimatter. Where did it go? The answer might lie in CP violation, a subtle asymmetry in the laws of physics discovered in the 1960s. Some particles decay differently depending on whether they're matter or antimatter, creating a slight preference for matter. This tiny bias, amplified over billions of years, could explain why matter won. But the CP violation we've observed isn't strong enough to account for the entire asymmetry. There must be additional sources of CP violation, new physics beyond the standard model that we haven't discovered yet. Now let's discuss the Planck units. These are the natural units of measurement in physics, derived from fundamental constants. The speed of light, the gravitational constant, Planck's constant, and the Boltzmann constant. The Planck length is about 10 to the power of negative 35 meters, the smallest length that has physical meaning. The Planck time is about 10 to the power of negative 43 seconds, the smallest time interval. At scales smaller than these, quantum effects of gravity dominate, and space-time itself becomes uncertain. The Planck units set the scale where we need a theory of quantum gravity, and they're far beyond anything we can probe experimentally. The Large Hadron Collider probes distances of about 10 to the power of negative 19 meters, about 16 orders of magnitude larger than the Planck length. To probe the Planck scale directly, we'd need an accelerator larger than the galaxy. Let's explore the idea that the universe might be cyclic. In this model, the Big Bang wasn't the beginning. It was a transition from a previous collapsing phase. The universe undergoes endless cycles of expansion and contraction, each cycle lasting trillions of years. This avoids the problem of the initial singularity. There is no beginning. The universe is eternal, cycling forever. But the details are murky. What happens at the bounce? Does information survive from one cycle to the next? Do the physical constants change? We don't have a complete theory of cyclic cosmology, but it's an active area of research, and it might provide an alternative to inflation and the multiverse. Now let's talk about magnetic monopoles. In classical electromagnetism, you can't have a magnetic north pole without a south pole. Magnets always come in pairs. But some theories, including grand unified theories, predict that magnetic monopoles, isolated north or south poles, should exist. They might have been created in the early universe during phase transitions, but we've never found one. Inflation might explain why. If monopoles were created before inflation, the exponential expansion would dilute them to such low densities that finding one would be incredibly unlikely. They're out there, but spread so thinly across the universe that we might never see one. Let's discuss cosmic expansion in more detail. When we say the universe is expanding, we don't mean galaxies are moving through space. We mean space itself is stretching, carrying galaxies along with it. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they're traveling across the surface, but because the surface is expanding. That's what's happening to the universe. And the expansion has a strange property. The farther apart two galaxies are, the faster they're receding from each other. This is Hubble's law, and it's a direct consequence of space expanding uniformly. Double the distance, double the recession velocity. At some point, galaxies are so far apart that space between them expands faster than light. This doesn't violate relativity because it's space that's expanding, not the galaxies moving through space. Those galaxies are beyond our cosmic horizon, permanently out of reach. Now let's return to consciousness from a different angle. Some physicists and philosophers propose that consciousness is an emergent phenomenon, arising from the complexity of information processing in the brain. Others argue that consciousness might be more fundamental, perhaps even a property of the universe itself. The integrated information theory, developed by Giulio Tononi, suggests that consciousness is related to integrated information, a measure of how much a system's parts are interconnected and interdependent. By this measure, any system that integrates information has some degree of consciousness. A thermostat has a tiny amount. A human brain has a lot. This implies that consciousness is not binary but exists on a spectrum, and it might not be unique to biological systems. If this theory is correct, then sophisticated artificial intelligences might be conscious. Not in the same way humans are, but in their own way. And it raises the question of moral consideration. If an AI is conscious, does it have rights? Can it suffer? These are not just philosophical questions. They're practical questions we'll need to answer as AI continues to advance. Let's talk about the concept of cosmic rays creating mutations in DNA. High-energy particles from space constantly bombard Earth, and when they interact with living tissue, they can damage DNA. Most of the time, the damage is repaired or the cell dies. But occasionally, the damage results in a mutation that survives and is passed on. Cosmic rays have been contributing to evolution for billions of years, introducing random changes that natural selection acts upon. We're all products of cosmic ray mutations in a very real sense. The universe is constantly experimenting with life, bombarding it with radiation, seeing what survives. Now let's explore the idea of cosmic voids in more detail. These are the largest structures in the universe, regions hundreds of millions of light years across containing almost no galaxies. They're not completely empty. There are a few galaxies, a few filaments of dark matter, but mostly it's just space. And they're growing. As the universe expands, voids expand faster than regions filled with matter because there's less gravity to slow them down. Eventually, in the far future, voids will dominate the universe, with islands of matter separated by vast empty spaces. The cosmic web will fragment, and the universe will become a lonely place. Let's discuss the Fermi paradox solutions in more detail. One possibility is the Great Silence. Maybe intelligent civilizations are common, but they don't communicate. Maybe they've moved beyond radio waves using technologies we can't detect. Or maybe they're deliberately quiet, hiding from potential threats. The dark forest hypothesis, from science fiction, suggests that the universe is full of civilizations, but everyone is silent because revealing yourself is dangerous. There might be predatory civilizations out there, and the safest strategy is to remain hidden. Another possibility is the rare Earth hypothesis. Maybe Earth is unusually well-suited for life. We're in the habitable zone of a stable star, in a galaxy with moderate star formation, in a solar system with a large moon that stabilizes our climate and a giant planet that shields us from asteroids. Maybe complex life requires so many lucky breaks that it's incredibly rare. Simple microbes might be common, but intelligent, technological civilizations might be almost unique. We might be alone or nearly alone in the galaxy. Or maybe the great filter is ahead of us. Maybe every civilization reaches a point where it develops technology capable of destroying itself, and very few survive. Nuclear weapons, climate change, artificial intelligence, nanotechnology, bioengineering. There are many ways to go extinct. Maybe the universe is littered with the ruins of civilizations that didn't make it. And maybe we're approaching that filter right now. The next few centuries will determine whether we join the ranks of the extinct or whether we survive to become a long-lasting, starfaring species. Now let's talk about the possibility of detecting gravitational waves from the Big Bang. During the inflationary epoch, quantum fluctuations in spacetime were amplified to cosmic scales, creating gravitational waves. These primordial gravitational waves are still out there, too weak to detect directly with current instruments, but they should have left an imprint on the cosmic microwave background. Detecting this imprint would confirm inflation and give us a glimpse of the universe at energies far beyond anything we can achieve with particle accelerators. It's one of the holy grails of cosmology, and experiments are being designed to search for it. Let's explore the concept of digital physics. This is the idea that the universe is fundamentally discrete, like a computer simulation. Spacetime is made of tiny pixels, time advances in discrete steps, and the laws of physics are computational rules that update the state of the universe. This isn't the same as the simulation hypothesis, which says we're in a computer. Digital physics says the universe itself is a computer processing information according to the laws of physics. It's a radical idea, but it has some support. Quantum mechanics is inherently discrete. Particles have quantized properties. Maybe spacetime is quantized too, made of tiny, indivisible units. If the universe is computational, then the limits of computation apply to the universe. There's a maximum amount of information that can be stored in a region of space, determined by the area of its boundary. There's a maximum rate at which information can be processed, determined by the energy available. These are called the Bekenstein bound and the Margulis-Levitin theorem, and they place fundamental limits on what the universe can do. No matter how advanced our technology becomes, we can never exceed these limits. They're built into the fabric of reality. Now let's discuss the idea of the universe as a quantum computer. Seth Lloyd and others have proposed that the universe isn't just computational but is literally a quantum computer processing quantum information. Every particle, every interaction is a quantum computation. The universe is constantly computing its own future, solving the Schrödinger equation step by step. In this view, the laws of physics are the software, and the universe is the hardware. And since quantum computers can solve certain problems exponentially faster than classical computers, the universe might be incredibly efficient at computing its own evolution. This raises a question. What is the universe computing? Is it solving a specific problem, or is it just running, exploring all possible states? Maybe the universe is searching for something, optimizing some cosmic function we don't understand yet. Or maybe it's not computing anything. Maybe it's just evolving, and the computational framework is just a useful way for us to think about it. Let's talk about the possibility of faster-than-light communication. We've said you can't send information faster than light, but what about quantum entanglement? When two particles are entangled, measuring one instantly affects the other, no matter the distance. Doesn't that allow for faster-than-light communication? No. The results of measurements on entangled particles are random. You can't control what you get, and the person at the other end also gets random results. It's only when you compare your results traveling at normal speeds that you see the correlation. You can't use entanglement to send a message faster than light. The universe preserves causality. Now let's explore the concept of entropy in black holes. When you throw matter into a black hole, the matter carries entropy. But where does that entropy go? According to the second law of thermodynamics, entropy can't decrease. So the entropy must go somewhere. Hawking and Bekenstein realized that black holes themselves have entropy proportional to the area of their event horizon. When matter falls in, the black hole's horizon grows, and its entropy increases. The second law is preserved. But this means black holes are thermodynamic objects with temperature and entropy, blurring the line between gravity and thermodynamics. Let's discuss the heat death of the universe in more detail. In the far future, if dark energy continues driving the expansion, stars will burn out, galaxies will fade, and the universe will become cold and dark. Black holes will evaporate through Hawking radiation, taking quadrillions of years. Eventually, even protons might decay, if theories of grand unification are correct, leaving only photons and leptons. The universe will reach maximum entropy, a state of perfect equilibrium where nothing changes, nothing happens. This is heat death, the ultimate fate of a universe dominated by dark energy. It's not a dramatic end. It's a slow fade into eternal darkness and stillness. But heat death might not be the end. Quantum fluctuations continue even in a maximal entropy state. Over unimaginably long timescales, these fluctuations might create new regions of low entropy, new big bangs, new universes. The multiverse might be eternal, constantly creating and destroying universes in an endless cycle. Or maybe there's a deeper principle we don't understand yet that prevents heat death or transforms it into something new. Now let's talk about the concept of symmetry in physics. The laws of physics are symmetric. They don't change if you rotate your experiment, if you move it to a different location, or if you perform it at a different time. These symmetries are fundamental, and they lead to conservation laws through Noether's theorem. Symmetry under translations in space leads to conservation of momentum. Symmetry under translations in time leads to conservation of energy. Symmetry under rotations leads to conservation of angular momentum. Every conservation law is tied to a symmetry, and every symmetry reflects a deep structure in the laws of physics. But symmetries can be broken. In the early universe, at high energies, all forces were unified, governed by a single symmetric theory. As the universe cooled, symmetries broke, and the forces separated. The electromagnetic and weak nuclear forces were once unified in the electroweak force, but below a certain energy, the symmetry broke, and they became distinct. Symmetry breaking is how the universe gains structure, how particles acquire mass, how forces differentiate. It's a fundamental process, and understanding it is key to understanding the evolution of the cosmos. Let's explore the idea of white holes. These are the time-reversed versions of black holes. While nothing can escape from a black hole, nothing can enter a white hole. They're predicted by general relativity, but we've never seen one. They might not exist in nature, or they might be incredibly rare, appearing only in exotic situations like the Big Bang or the interiors of black holes. Some theories suggest that the Big Bang itself was a white hole, a fountain of matter and energy erupting into space-time. If true, every black hole might be connected to a white hole in another part of the universe, or another universe entirely. Now let's discuss the concept of quantum teleportation. This isn't teleportation in the science fiction sense. You can't transport matter or people, but you can transport quantum information. Using entanglement, you can transfer the quantum state of one particle to another distant particle without the information traveling through the space in between. It's instantaneous, but it requires a classical communication channel to complete the process, so it doesn't violate relativity. Quantum teleportation is used in quantum computing and quantum cryptography, and it's a fascinating demonstration of the weird properties of entanglement. Let's explore the far future of the universe in more scenarios. If dark energy weakens over time, the expansion might slow, and the universe could eventually recollapse in a big crunch. All matter and energy would be pulled back together, compressing into a singularity. This could be the end, or it could trigger a new Big Bang, starting the cycle over. If dark energy strengthens, the universe might end in a big rip, where the expansion accelerates so much that galaxies, stars, planets, atoms, everything is torn apart. The universe would disintegrate, leaving only fundamental particles in an ever-expanding void. Or maybe the universe continues expanding forever, cooling indefinitely. In this scenario, intelligent beings far in the future might find ways to survive by harvesting energy from black holes, from the quantum vacuum, or from other exotic sources. They might exist as digital consciousnesses, uploaded into computers powered by the rotational energy of black holes, thinking incredibly slowly to conserve energy, stretching their existence over trillions upon trillions of years. Civilization might persist far longer than stars, adapting to an ever colder, darker universe. Life, or something like it, might find a way to endure until the very end of time. Conclusion: we've journeyed through the cosmos, exploring theories that challenge everything we thought we knew about reality. From the multiverse to black holes, from quantum mechanics to the fate of the universe, we've seen that the cosmos is stranger, more beautiful, and more mysterious than we ever imagined. We've learned that time is relative, that space might be a hologram, that consciousness might be fundamental, and that we're made of stardust, literally children of the universe. But here's the truth: we've barely begun. Every answer we found has revealed 10 new questions. Every theory we've tested has pointed to deeper mysteries. The universe is vast beyond comprehension, and we've explored only the tiniest fraction of it. There are countless galaxies we'll never see, countless stars we'll never visit, countless phenomena we haven't even discovered yet. And that's okay. That's the beauty of science. It's not about having all the answers. It's about asking better questions. So what's next? The future of physics lies in the unknown. Dark matter, dark energy, quantum gravity, the multiverse, consciousness. These are the frontiers, the puzzles that will occupy scientists for generations to come. And who knows? Maybe someone listening to these words will be the one to solve them. Maybe you'll be the one to discover the theory of everything, to unravel the mysteries of black holes, to prove the multiverse exists. The universe is waiting. The questions are there. And the only limits are the ones we place on ourselves. We're living in a golden age of discovery. We've detected gravitational waves, imaged black holes, found thousands of exoplanets, and mapped the cosmic microwave background with extraordinary precision. We're on the verge of even greater breakthroughs. Quantum computers are becoming a reality. Telescopes more powerful than ever are being built. Missions to Mars, to the outer solar system, to the stars themselves are being planned. The future is bright, and it's filled with possibilities. But we also face challenges. Climate change, existential risks, the threat of self-destruction. The next few centuries will determine whether humanity survives to explore the cosmos or whether we become just another extinct species, a brief flicker in the long history of the universe. The choice is ours. We can work together, solve our problems, and reach for the stars. Or we can turn inward, focus on short-term gains, and let the future slip away. I know what I believe. I believe in humanity's potential. I believe in our curiosity, our creativity, our resilience. We've come so far in such a short time. A few centuries ago, we didn't even know other galaxies existed. Now we're talking about the multiverse, about time travel, about the nature of consciousness itself. We've learned so much, and there's so much more to learn. The cosmos is calling, and it's up to us to answer. So the next time you look up at the night sky, remember this. Those stars are not just distant points of light. They're suns, like ours, potentially orbited by planets, perhaps home to life. They're forges where the elements of your body were created. They're markers of the vast scale of the universe, reminders that we're part of something infinitely larger than ourselves. And they're beacons of possibility, signs that the universe is full of wonders waiting to be discovered. You're not just an observer. You're a participant. You're part of the cosmos, a way for the universe to know itself, to experience its own existence. And that's extraordinary. That's a gift. So use it. Ask questions. Seek answers. Wonder. Dream. Explore. Because in doing so, you're not just living your life. You're participating in the grandest adventure of all. The adventure of understanding. The adventure of discovery. The adventure of being part of a universe that's stranger, more beautiful, and more mysterious than anyone ever imagined. Welcome to the cosmos. You're home, and the universe is waiting for you to explore it. But let's not stop there, because there's an entirely different dimension to this story, one that takes us even deeper into the fabric of reality. We've talked about what the universe is, but now let's talk about how we know what we know. Let's explore the quantum measurement problem, the observer effect, and the strange relationship between consciousness and physical reality. In quantum mechanics, particles exist in superposition until they're measured. But what counts as a measurement? Does it require a conscious observer, or is any interaction enough? This is the measurement problem, and it's been debating physicists for a century. Niels Bohr thought measurement was a fundamental process that couldn't be reduced to physics. The act of observation causes the wave function to collapse, turning possibilities into actualities. But what is observation? What makes it special? John von Neumann proposed that consciousness is necessary for wave function collapse. The chain of quantum interactions continues, everything remaining in superposition, until a conscious mind observes the result. This seems to give consciousness a special role in physics, a role most physicists are uncomfortable with. But the alternative is strange too. If consciousness isn't required, then when does collapse happen? Where do you draw the line between the quantum world and the classical world? Hugh Everett's many worlds interpretation sidesteps this problem by saying there is no collapse. Every possibility happens in separate branches of reality. You don't need consciousness. You don't need measurement. The universe just keeps splitting, and you experience one branch while other versions of you experience other branches. It's elegant in some ways, profligate in others. Every quantum event creates countless new universes. The multiverse becomes incomprehensibly vast. But there's another interpretation that's gaining traction. Quantum decoherence explains why we see definite outcomes without invoking collapse or multiple worlds. When a quantum system interacts with its environment, information leaks out, spreading through countless particles. The system becomes entangled with its surroundings, and the coherent superposition is destroyed. From the inside, it looks like collapse, but it's really just the system becoming correlated with the environment. Decoherence happens incredibly fast, in billionths of a second, which is why we don't see quantum superpositions in everyday life. Decoherence doesn't solve the measurement problem completely, but it pushes it back. It explains why we see definite outcomes, but it doesn't explain why we see the particular outcome we do. That remains mysterious. Some physicists think quantum mechanics is incomplete, that there are hidden variables we haven't discovered yet. David Bohm proposed pilot wave theory, where particles have definite positions at all times, guided by a quantum wave. The wave is real, but so is the particle. There's no randomness, no collapse, just deterministic evolution of particle positions guided by the wave. It reproduces all the predictions of quantum mechanics, but it requires faster-than-light connections between particles, which most physicists find unpalatable. Let's talk about Wheeler's delayed choice experiment. This is one of the most mind-bending experiments in quantum mechanics. Light passes through a double-slit apparatus. If you don't measure which slit it went through, you see an interference pattern, evidence that light behaves like a wave, passing through both slits. If you do measure which slit it went through, the interference pattern disappears, and light behaves like a particle going through one slit or the other. So far, so quantum. But here's the twist. You can delay the choice of whether to measure until after the light has already passed through the slits. You'd think the light has already decided whether to be a wave or a particle. But quantum mechanics says no. The choice you make now affects what happened in the past. The light retroactively becomes a wave or a particle depending on your future measurement. This has been tested in laboratories, and the results confirm the prediction. The past is not fixed until you observe it. Reality is fundamentally observer-dependent. This leads to even stranger ideas. The quantum eraser experiment shows that you can make the interference pattern reappear even after you've measured which slit the light went through by erasing the witch path information. It's as if the universe keeps track of what information is available and adjusts reality accordingly. Information, not matter, not energy, seems to be fundamental. John Wheeler, one of the great physicists of the 20th century, proposed the concept of it from bit. The idea that every physical quantity, every particle, every force, derives from information. The universe is not made of stuff. It's made of bits, of answers to yes or no questions. Matter and energy emerge from information. This is a radical reconceptualization of reality, one that's gaining support from developments in quantum information theory and black hole physics. Wheeler also proposed the participatory anthropic principle. He suggested that observers are not just passive witnesses but active participants in the creation of reality. The universe doesn't exist independently of observation. It requires observers to make it real. This sounds mystical, but Wheeler was a hard-nosed physicist, and he based this idea on the mathematics of quantum mechanics. In his view, we're not just in the universe. We're bringing the universe into existence by observing it. Now let's explore the Penrose-Hameroff theory of consciousness. Roger Penrose, a mathematical physicist, and Stuart Hameroff, an anesthesiologist, proposed that consciousness arises from quantum processes in microtubules, tiny structures inside neurons. They argue that the brain is a quantum computer processing information at the quantum level, and that consciousness is a result of quantum state reduction, a kind of objective collapse of the wave function that doesn't require an external observer. The theory is called orchestrated objective reduction, or orchestroir. Most neuroscientists are skeptical. The brain is warm, wet, and noisy, conditions that should destroy quantum coherence in nanoseconds. But Hameroff argues that microtubules might protect quantum states long enough for quantum computation to occur. And there's some evidence for quantum effects in biology. Photosynthesis uses quantum coherence to transfer energy efficiently. Birds might use quantum entanglement for navigation, detecting Earth's magnetic field through quantum processes in their eyes. Enzymes might use quantum tunneling to speed up chemical reactions. The boundary between quantum and classical is blurrier than we thought. If consciousness does have a quantum component, it might explain why it's so hard to understand. Classical physics can't capture it. You need quantum mechanics with its superpositions and entanglements and non-locality. Consciousness might be fundamentally quantum, and that's why it seems so different from ordinary matter. This is speculative, but it's a reminder that we don't fully understand consciousness, and quantum mechanics might hold clues. Let's shift to cosmology and talk about the Hubble tension. We measure the expansion rate of the universe in two ways. One is by looking at the cosmic microwave background and using cosmological models to infer the current expansion rate. The other is by measuring the distances and velocities of nearby galaxies and supernovae. The problem is, these two methods give different answers. The local measurements give a higher expansion rate than the CMB predicts. The discrepancy is small, but it's statistically significant, and it's been confirmed by multiple independent studies. This is the Hubble tension, and it's one of the biggest puzzles in cosmology. Either one of the measurements is wrong, which seems unlikely given how carefully they've been done, or our cosmological model is incomplete. Maybe dark energy is more complicated than we thought. Maybe it evolves over time instead of being constant. Maybe there's new physics we haven't accounted for. Or maybe the universe is not as uniform as we assume, and local peculiarities affect our measurements. Resolving the Hubble tension might require a revolution in cosmology, new theories that go beyond the standard model of the Big Bang. Now let's talk about modified gravity theories. What if dark matter doesn't exist? What if, instead, our understanding of gravity is wrong on galactic scales? This is the idea behind modified Newtonian dynamics, or MOND. Mordechai Milgram proposed in the 1980s that gravity behaves differently when accelerations are very small, like at the edges of galaxies. Instead of force being proportional to acceleration, as in Newton's laws, the relationship changes at low accelerations. This modification can explain the rotation curves of galaxies without dark matter. MOND works surprisingly well for galaxies, but it struggles with galaxy clusters and cosmology. It can't explain gravitational lensing observations or the cosmic microwave background without invoking some dark component. So most physicists favor dark matter. But MOND refuses to die. Some researchers are developing relativistic versions of MOND, theories that modify general relativity instead of Newtonian gravity. These theories are complex and not fully developed, but they're a reminder that dark matter, while well supported, is not the only possibility. Let's discuss the bullet cluster, one of the strongest pieces of evidence for dark matter. The bullet cluster is actually two galaxy clusters that collided and passed through each other. When they collided, the gas in the clusters, which is most of the normal matter, slammed together and was slowed down by friction. But the galaxies themselves, which make up a tiny fraction of the mass, pass through almost unaffected. Gravitational lensing reveals where the mass is, and it's not where the gas is. It's where the galaxies are. This suggests that most of the mass is dark matter, which passed through the collision without interacting, following the galaxies. This is hard to explain with modified gravity. MOND predicts that the mass should be where the normal matter is, but observations show otherwise. The bullet cluster is one of the clearest demonstrations that something invisible, something that interacts only through gravity, is out there. Dark matter might not be the only explanation, but it's the best one we have. Now let's explore emergent gravity, an idea proposed by Eric Verland. He suggests that gravity is not a fundamental force but an emergent phenomenon, like temperature or pressure. At the microscopic level, there's no such thing as temperature. Temperature emerges from the average motion of countless molecules. Similarly, Verland argues that gravity emerges from the entropy of information on the holographic screens that surround every object. You don't need gravitons, particles that carry the gravitational force. Gravity is an entropic force, a statistical effect that emerges from the way information is distributed in spacetime. Emergent gravity can reproduce Newton's laws and aspects of general relativity, and it might explain dark matter without invoking new particles. Verland claims that what we call dark matter is actually a consequence of how entropy behaves in the universe. The extra gravitational pull we attribute to dark matter is really an emergent effect of the holographic structure of spacetime. This is controversial and not widely accepted, but it's an example of how radical rethinking can lead to new ideas. Let's talk about supersymmetry. This is the idea that every particle has a superpartner with different spin. Electrons have selectrons, quarks have squarks, photons have photinos. Supersymmetry would double the number of particles, but none of the superpartners have been discovered yet. If they exist, they're heavier than anything we can produce in current accelerators, or they interact so weakly that we can't detect them. Supersymmetry is appealing because it solves several problems. It stabilizes the mass of the Higgs boson, preventing quantum corrections from making it absurdly heavy. It unifies the strengths of the forces at high energies, suggesting a grand unified theory. And the lightest supersymmetric particle is stable and interacts weakly, making it a perfect dark matter candidate. But so far, there's no evidence for supersymmetry. The Large Hadron Collider has searched extensively and found nothing. Either supersymmetry is broken at higher energies than we can reach, or it's wrong. The physics community is divided on whether to keep pursuing it or to look elsewhere. Now let's discuss grand unification. The standard model of particle physics describes three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. These forces have different strengths, but at high energies, their strengths converge. This suggests that they might unify into a single force, the way electromagnetism and the weak force unify into the electroweak force at high energies. Grand unified theories, or GUTS, attempt to describe this unification. GUTS predict that protons are not stable. They should decay very slowly over timescales of 10 to the power of 34 years or more. We've been searching for proton decay for decades, using huge detectors filled with ultrapure water, watching for the flash of light that would signal a proton decaying. So far, nothing. Protons live longer than the current age of the universe by many orders of magnitude, and if they do decay, it's even slower than many GUTS predict. This has ruled out some versions of grand unification, but others remain viable. GUTS also predict magnetic monopoles, isolated magnetic poles, which we've never found. Inflation might explain their absence, diluting them to undetectable densities. Grand unification remains an attractive idea, but without experimental evidence, it's just a beautiful mathematical structure that might or might not describe reality. Let's explore the theory of everything. Physicists dream of a single theory that unifies all four forces, including gravity, and explains all particles and interactions. String theory is one candidate. Loop quantum gravity is another, but there are others. Some researchers are exploring causal dynamical triangulation, which builds spacetime from tiny simplices, like a lattice of triangles. Others are investigating causal sets, where spacetime is made of discrete points connected by causal relations. And some think the answer lies in twistor theory, a mathematical framework developed by Roger Penrose that describes spacetime in terms of light rays. We don't know which, if any, of these approaches will succeed. The theory of everything might require entirely new mathematics, concepts we haven't invented yet. Or it might turn out that there is no theory of everything, that physics is an endless tower of effective theories, each valid in its own domain, with no ultimate foundation. That would be disappointing, but it's a possibility we have to consider. Now let's talk about the black hole information paradox in more depth. This problem has driven theoretical physics for decades, and recent developments suggest we're close to a solution. The paradox arises because Hawking radiation is thermal, meaning it contains no information about what fell into the black hole. If the black hole evaporates completely, the information is lost, violating quantum mechanics. But in 2019, physicists calculated something called the Page curve, which tracks how information escapes from a black hole over time. Using techniques from string theory and holography, they found that information does escape, encoded in subtle correlations in the Hawking radiation. The key insight involves quantum entanglement and wormholes. In a breakthrough, physicists showed that entanglement between particles is mathematically equivalent to tiny wormholes connecting them. This is the ER equals EPR conjecture, named after Einstein and Rosen, who discovered wormholes, and Einstein, Podolsky, and Rosen, who discovered entanglement. If entanglement is actually a wormhole, then the geometry of spacetime and quantum entanglement are two sides of the same coin. Space emerges from entanglement. This is a profound unification of gravity and quantum mechanics, and it might be the key to understanding black holes. Using these ideas, physicists discovered that information escapes through what are called quantum extremal surfaces, boundaries in spacetime where quantum and gravitational effects balance. These surfaces can extend inside the black hole, capturing information and allowing it to leak out. The black hole doesn't lose information after all. It's just incredibly scrambled, encoded in the radiation in ways that are almost impossible to decode. The information paradox might finally be solved, not by overthrowing Hawking's calculation, but by understanding it more deeply through the lens of quantum gravity. Let's discuss the firewall paradox, a related problem that emerged in 2012. The paradox asks what happens at the event horizon. According to general relativity, nothing special. You cross it smoothly, not even noticing. But according to quantum mechanics, if information escapes in Hawking radiation, the radiation must be entangled with the interior of the black hole. But it's also entangled with earlier radiation that already escaped. A particle can't be maximally entangled with two different systems. That violates the rules of quantum mechanics. The only way to break the entanglement is for the horizon to become a wall of high-energy particles, a firewall that incinerates anything trying to cross. But this contradicts general relativity, which says the horizon is smooth. The firewall paradox forced physicists to rethink their assumptions. Some proposed black hole complementarity, the idea that different observers see different things. Someone falling in sees a smooth horizon and falls to their doom at the singularity. Someone staying outside sees them hit a firewall at the horizon and get incinerated. Both descriptions are valid, and they don't contradict each other because the two observers can never compare notes. This sounds like a cheat, but it's consistent with the holographic principle. The information is encoded on the horizon, and different observers decode it differently. Recent work suggests the firewall paradox might be resolved by islands, regions inside the black hole that are secretly part of the radiation's entanglement structure. Using replica wormholes, hypothetical spacetime connections that exist in certain quantum calculations, physicists have shown that the paradox can be avoided. The horizon remains smooth, information escapes, and quantum mechanics is preserved. It's a technical solution involving advanced mathematics, but it represents real progress in understanding quantum gravity. Now let's talk about the holographic principle in more detail, because it's central to modern theoretical physics. The holographic principle states that all the information in a volume of space can be encoded on the boundary of that volume. It's as if the three-dimensional universe is a hologram projected from a two-dimensional surface. This idea came from black hole thermodynamics and has been developed through the ADS-CFT correspondence, a duality discovered by Juan Meldacena. ADS-CFT is a concrete realization of holography. It relates a theory of gravity in a space called anti-de Sitter space to a quantum field theory without gravity on the boundary of that space. It's a dictionary between two different theories, and it's been tested extensively. Calculations that are hard in one theory are easy in the other, and the results match. This suggests that gravity and quantum mechanics are not separate. Gravity is quantum mechanics, viewed from a different perspective. Spacetime emerges from entanglement in the boundary theory. This has profound implications. It means space itself is not fundamental. It's emergent, constructed from quantum information. Distance, locality, even the number of dimensions might be illusions, artifacts of how we perceive the underlying quantum structure. At the deepest level, the universe is not a collection of particles moving through space. It's a network of quantum correlations, and space is a convenient way to organize those correlations. Let's explore quantum complexity and its connection to black holes. Complexity is a measure of how hard it is to prepare a quantum state. A simple state, like all qubits in the ground state, has low complexity. A highly entangled state, where qubits are correlated in intricate ways, has high complexity. Preparing such a state requires many quantum gates, many operations. Complexity grows over time as a quantum system evolves. Physicists have discovered that the complexity of a quantum state is related to the geometry inside a black hole. As the black hole evaporates, the interior doesn't shrink. It grows, expanding into an ever larger region of spacetime. This growth is due to the growing complexity of the Hawking radiation. The interior of a black hole is not a place in the usual sense. It's a representation of the computational complexity of the quantum state of the radiation. Spacetime inside the horizon emerges from the complexity of the boundary theory. This connection between complexity and geometry is leading to new insights about quantum gravity. It suggests that understanding black holes requires understanding quantum computation, information theory, and complexity theory. The universe might be a quantum computer, and black holes are its most complex states. Studying them teaches us about the limits of computation, the nature of entropy, and the structure of spacetime. Now let's talk about fast radio bursts. These are mysterious signals from deep space, incredibly bright flashes of radio waves lasting just milliseconds. They were discovered in 2007, and for years we had no idea what caused them. Theories ranged from neutron star collisions to evaporating black holes to alien civilizations. Most FRBs are one-time events, but some repeat, flashing over and over with irregular timing. In recent years, we've localized several FRBs to distant galaxies, billions of light-years away. We've even detected one in our own galaxy, coming from a magnetar, a neutron star with an incredibly strong magnetic field. This suggests that at least some FRBs are caused by magnetars, though the exact mechanism is still unclear. When a magnetar undergoes a starquake, its crust shifting suddenly, it can release a burst of energy that produces the radio signal. But we're not sure this explains all FRBs. Some might have different origins. The mystery is not fully solved, and every new FRB we detect adds to the puzzle. Let's discuss magnetars in more depth. These are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's, the most powerful magnetic fields in the universe. The field is so strong that it warps the shape of atoms, turning them into elongated needles. It affects the vacuum itself, creating a phenomenon called vacuum polarization, where virtual particles align with the field. If you got within 1,000 kilometers of a magnetar, the magnetic field would disrupt the electrical activity in your neurons, shut down your brain, and kill you instantly. From farther away, the field would tear apart molecular bonds, dissociating your body into atoms. Magnetars are powered by their magnetic fields, which decay over time, releasing energy as X-rays and gamma rays. They flare unpredictably, sometimes releasing more energy in 1/10 of a second than the sun emits in a year. The most powerful flare ever recorded, in 2004, came from a magnetar 30,000 light-years away and briefly saturated gamma-ray detectors across the solar system. If a magnetar flared that strongly within 10 light-years of Earth, it could trigger a mass extinction, stripping away the ozone layer and exposing the surface to deadly ultraviolet radiation. Fortunately, there are no magnetars that close. Now let's explore strange stars and quark stars, hypothetical objects even more exotic than neutron stars. Inside a neutron star, matter is compressed so much that protons and electrons merge into neutrons. But if you compress it even more, neutrons themselves might break apart into their constituent quarks. The result would be quark matter, a soup of up, down, and strange quarks, flowing freely without being confined inside protons and neutrons. A quark star would be incredibly dense, even denser than a neutron star, and it would look similar from the outside. We might have already observed quark stars without realizing it, mistaking them for neutron stars. There's also the possibility of strange matter, a state of matter made of up, down, and strange quarks in roughly equal numbers. Strange matter might be more stable than ordinary matter, meaning that once it forms, it's lower in energy than protons and neutrons. This raises a terrifying possibility. If you brought strange matter into contact with a neutron star, it would convert the star into strange matter, releasing energy and creating more strange matter in a runaway reaction. The entire star would transform in seconds. And if a chunk of strange matter, a strangelet, hit Earth, it could convert the entire planet into strange matter, destroying all life instantly. Don't worry, though. Strange matter probably doesn't exist, and even if it does, cosmic ray collisions would have created it long ago, and we'd have seen the effects. The fact that we're still here suggests strange matter is either non-existent or not as dangerous as the theory suggests. Let's talk about Penrose's conformal cyclic cosmology, another alternative to the Big Bang. Roger Penrose proposes that the universe undergoes infinite cycles, but not through big crunches and bounces. Instead, in the far future, when all matter has decayed and only massless particles remain, the universe loses all sense of scale. Without massive particles, there's no way to measure size or time. The universe becomes conformal, scale invariant. At this point, the geometry of the far future becomes mathematically identical to the geometry of the Big Bang. The end of one cycle is the beginning of the next, not through a physical transition but through a mathematical identification. Time is infinite, but it's divided into epochs called eons, each starting with a Big Bang and ending in infinite expansion. Penrose claims that this theory makes testable predictions. Collisions between supermassive black holes in previous eons should leave imprints on the cosmic microwave background, circular patterns of correlated temperature fluctuations. He's reported seeing these patterns in the data, but most cosmologists are skeptical. The patterns could be statistical flukes, artifacts of how we process the data. Conformal cyclic cosmology is beautiful mathematically, but it's not clear whether it describes reality. Now let's discuss the landscape problem in string theory. String theory allows for an enormous number of possible vacuum states, different ways the extra dimensions can be compactified, each corresponding to a different universe with different physical laws. Estimates suggest there are 10 to the power of 500 possible vacua, maybe more. This is the string landscape, and it's both a blessing and a curse. It might explain why our universe has the properties it does. We're in one particular vacuum out of countless possibilities. But it also means string theory doesn't predict anything specific. Any observation can be accommodated by choosing the right vacuum. This makes string theory hard to test and has led some critics to argue it's not science but metaphysics. String theorists respond that the landscape is a feature, not a bug. Combined with eternal inflation, it leads naturally to the multiverse. Different regions of the multiverse have different vacuum states, different physical laws. We observe the laws we do because we exist in a region where those laws allow for life. It's anthropic reasoning again, and it's controversial. Some physicists embrace it. Others reject it, arguing that physics should explain why the laws are what they are, not just say they could be anything. Now let's explore swampland conjectures, recent developments in string theory that might constrain the landscape. The swampland is the set of theories that look consistent at low energies but can't be completed to a consistent quantum gravity theory. Swampland conjectures are principles that distinguish theories in the landscape from theories in the swampland. For example, the weak gravity conjecture says that gravity must always be the weakest force. Any charged particle must have a charge-to-mass ratio at least as large as an extremal black hole. If this is true, It rules out certain kinds of dark matter and certain mechanisms for inflation. These conjectures are not proven, but they're supported by many examples in string theory. If they're correct, they dramatically narrow the landscape, ruling out vast regions of possible universes. They might even make testable predictions about dark energy, inflation, or the masses of particles. Swampland conjectures represent a new direction in string theory, moving away from the anything-goes attitude of the landscape toward more definite predictions. Let's talk about the Transplanckian problem in inflation. During inflation, quantum fluctuations are stretched from subplanckian scales, smaller than the Planck length, to cosmic scales larger than galaxies. But we don't have a theory of physics at subplanckian scales. We don't know if space-time is continuous, quantized, or something else entirely. So how can we trust predictions about inflation if they depend on physics we don't understand? This is the Transplanckian problem, and it's a serious concern for inflationary cosmology. Some physicists argue that the details of subplanckian physics don't matter. Inflation washes out most of the details, leaving only general features like the spectrum of fluctuations. Others worry that we're building a theory on a foundation we don't understand, and it might collapse once we learn more about quantum gravity. It's an open question, and resolving it might require a complete theory of quantum gravity. Now let's discuss varying constants, the idea that the fundamental constants of nature might change over time or space. The speed of light, the charge of the electron, the strength of gravity, these are all assumed to be constant. But what if they're not? Some cosmological theories, including string theory, predict that constants can vary. If they do, we might be able to detect it by looking at distant galaxies, where light left billions of years ago. If the fine structure constant, which determines the strength of electromagnetism, was slightly different then, it would affect the spectrum of light from those galaxies. There have been controversial claims of detecting variations in the fine structure constant, but they're not confirmed. Most physicists think the constants are truly constant, but the possibility remains open. If they do vary, it would revolutionize physics. Constants wouldn't be fundamental parameters. They'd be fields, dynamic quantities that evolve along with the universe. Let's explore chameleon fields, a proposed solution to the cosmological constant problem. Chameleon fields are scalar fields that change their properties depending on the local environment. In regions of high density, like on Earth, the field has a large mass and a short range, making it invisible. In regions of low density, like intergalactic space, the field has a small mass and a long range, affecting the expansion of the universe. A chameleon field could act like dark energy on cosmological scales while remaining undetected in laboratory experiments. This is an example of a screening mechanism, a way for new physics to hide in plain sight. If dark energy is a chameleon field, it would explain why we see its effects on the universe but can't detect it locally. Experiments are searching for chameleon fields by looking for tiny forces that depend on the environment, but so far, nothing has been found. Now let's talk about cosmic natural selection, an idea proposed by Lee Smolin. He suggests that universes reproduce through black holes. Every black hole creates a new universe, a baby universe budding off from our own, with slightly different physical constants. The constants are inherited from the parent universe but can mutate slightly, like genes in biology. Universes that produce many black holes have many offspring, passing on their constants. Over time, the multiverse becomes dominated by universes fine-tuned to produce black holes, which requires stars, which requires the right constants for nuclear fusion and stellar evolution. This would explain why our universe has the properties it does. We're descendants of a long line of universes optimized to produce black holes. It's a form of cosmic Darwinism, natural selection applied to universes. It's speculative and hard to test, but it's a fascinating example of how evolutionary thinking can be applied to cosmology. Let's discuss quantum Darwinism, a related idea that explains why we see a classical world emerging from quantum mechanics. In the quantum world, systems exist in superpositions, but we never see superpositions in everyday life. Quantum Darwinism explains this through decoherence and redundancy. When a quantum system interacts with its environment, information about the system is copied into many particles in the environment. This redundant information can be accessed by many observers, and it defines the classical state. States that are robust, that get copied many times, survive. States that are fragile, that don't get copied, disappear. The classical world emerges through a process analogous to natural selection, where only the fittest quantum states survive. This is a powerful idea because it explains objectivity. We all see the same classical world because we're all accessing the same redundant information encoded in the environment. Quantum mechanics is not about individual systems. It's about correlations between systems, and those correlations, when they're redundant and robust, give rise to the classical reality we experience. Now let's explore the quantum Zeno effect, a strange phenomenon where observation can freeze a quantum system. In quantum mechanics, systems evolve continuously, transitioning between states. But if you measure the system repeatedly, checking whether it's changed, the act of measurement can prevent the transition from happening. The system gets stuck, unable to evolve. This is the quantum Zeno effect, named after Zeno's paradox about motion. It's been demonstrated experimentally, and it has applications in quantum computing, where it's used to protect quantum information from noise. The effect is counterintuitive. You'd think measuring a system doesn't affect its evolution, but in quantum mechanics, measurement is an interaction, and interactions change the state. By measuring frequently, you keep collapsing the wave function, resetting the system before it has time to evolve. It's a reminder that in quantum mechanics, observation is not passive. Observers participate in creating reality. Let's talk about the measurement problem in more detail. This is really the heart of quantum mechanics, the question that refuses to go away. When you measure a quantum system, you get a definite outcome, but before measurement, the system is in a superposition of all possible outcomes. How does the system choose? Quantum mechanics gives you probabilities, but it doesn't tell you why you get the particular result you do. This is the measurement problem, and it's been debated for a century. The Copenhagen interpretation, developed by Bohr and Heisenberg, says that the wave function is not a real object but a tool for calculating probabilities. Measurement causes collapse, but collapse is not a physical process. It's just an update of your knowledge. Many physicists find this unsatisfying because it doesn't explain what measurement is or why collapse happens. It treats measurement as fundamental, something that can't be reduced to physics. The many worlds interpretation, as we've discussed, says there is no collapse. Every outcome happens in a different branch of the universe. You see one outcome, but other versions of you see other outcomes. This avoids the measurement problem but creates a new problem. Why does it feel like only one outcome happens? Why do you experience a single world when the theory says all possibilities are real? Objective collapse theories propose that collapse is a physical process caused by gravity or other mechanisms. When a superposition becomes too massive or too spatially separated, collapses spontaneously without measurement. These theories modify quantum mechanics slightly, adding new terms to the equations. They make predictions that differ from standard quantum mechanics, and experiments are being designed to test them. So far, standard quantum mechanics is holding up. Relational quantum mechanics, proposed by Carlo Rovelli, says that quantum states are not absolute but relational. A system doesn't have a definite state by itself. It has a state relative to other systems. What looks like a superposition to you might look like a definite state to someone else, depending on your interaction with the system. There's no global wave function, only local descriptions from different perspectives. This avoids the measurement problem by denying that there's a problem. Quantum mechanics is fundamentally about relations, not absolutes. Cubism or quantum Bayesianism takes this even further. It says that the wave function is not a property of the world but a tool for making bets. It encodes your personal beliefs about the outcomes of measurements, updated according to Bayesian probability. Different observers can have different wave functions for the same system, and that's fine. Quantum mechanics is not about objective reality. It's about subjective experience and prediction. This is radically subjective, and most physicists are uncomfortable with it, but it's internally consistent and avoids many paradoxes. Now let's discuss pilot wave theory in more detail. This is also called de Broglie mechanics, and it's a deterministic interpretation of quantum mechanics. Particles have definite positions at all times, guided by a pilot wave that satisfies the Schrödinger equation. The wave is real, spreading through space, and it pushes particles along specific trajectories. There's no randomness in the particle's motion. The randomness we observe comes from our ignorance of the initial positions. Pilot wave theory reproduces all the predictions of quantum mechanics, but it has a cost. It requires non-locality. The pilot wave instantly affects particles across vast distances, violating the spirit of relativity. And the trajectories of particles are strange, looping and weaving in counterintuitive ways. Despite these issues, pilot wave theory is a viable interpretation, and it's favored by some physicists who prefer determinism to randomness. Let's explore information theory and its connection to physics. Information is physical. It takes energy to store information, and erasing information produces heat. This is Landauer's principle, discovered by Rolf Landauer in the 1960s. Every time you erase a bit of information, you must dissipate at least a tiny amount of energy into the environment. This connects information to thermodynamics. Entropy is not just disorder, it's missing information. Landauer's principle has been tested experimentally, and it holds. It means that computation is a physical process, subject to the laws of thermodynamics. There's a fundamental limit to how efficiently you can compute, determined by the energy cost of erasing bits. This has implications for the future of computing. As computers get smaller and more efficient, they approach these fundamental limits. Eventually, we'll hit a wall where further miniaturization is impossible because erasing bits would require more energy than we can dissipate. Now let's talk about Maxwell's demon, a thought experiment that seemed to violate the second law of thermodynamics. Imagine a tiny demon controlling a door between two chambers of gas. The demon lets fast molecules pass from left to right and slow molecules from right to left. Over time, the left chamber heats up and the right chamber cools down, decreasing entropy without doing work. This seems to violate thermodynamics. The resolution involves information. The demon must observe the molecules to decide which ones to let through. Observation requires storing information in the demon's memory. Eventually, the memory fills up, and the demon must erase it to continue. Erasing the memory produces entropy, at least as much as the demon decreased by sorting molecules. The second law is saved. You can't reduce entropy without paying an information cost. This connects thermodynamics, information, and computation in a deep way. Let's discuss self-organization and emergence. Complex systems can spontaneously organize into patterns, structures, and behaviors that aren't present in the individual components. Flocks of birds, schools of fish, traffic jams, ecosystems, economies, all exhibit emergent properties. The whole is more than the sum of the parts. This is emergence, and it's everywhere in nature. Self-organization happens in systems far from equilibrium, where energy flows through the system, maintaining order against the tendency toward disorder. Ilya Prigogine studied these dissipative structures and showed that they can form spontaneously, creating order out of chaos. Examples include convection cells in heated fluids, chemical oscillations in reactions, and patterns in sand dunes. Life itself is a dissipative structure, maintaining order by consuming energy and expelling waste. Emergence challenges reductionism, the idea that you can understand everything by breaking it down into parts. Sometimes you can't. The behavior of the whole can't be predicted from the behavior of the parts, not because the laws are different, but because the interactions are too complex. This suggests that there are multiple levels of description in nature, each valid in its own domain. Physics doesn't reduce to particles. Chemistry doesn't reduce to atoms. Biology doesn't reduce to molecules. Each level has its own principles, its own explanations, even though everything is ultimately made of the same stuff. Now let's explore chaos theory and fractals. Chaos is deterministic unpredictability. Simple systems, governed by simple rules, can exhibit behavior so complex that it's impossible to predict. The weather is chaotic. Small changes in initial conditions lead to vastly different outcomes. This is the butterfly effect. A butterfly flapping its wings in Brazil can set off a tornado in Texas. Not literally, but the idea is that tiny perturbations can amplify into massive effects. Chaotic systems are everywhere. The solar system is chaotic on long timescales. The orbits of planets are stable for millions of years but unpredictable over hundreds of millions. The Earth-Moon system is gradually evolving due to tidal forces, and the outcome depends sensitively on initial conditions. Chaos limits predictability. Even if we knew the laws of physics perfectly, we couldn't predict the future indefinitely because we can never measure initial conditions with perfect precision. Fractals are geometric shapes with self-similarity. Zoom in and you see the same patterns repeated at smaller scales. Coastlines, mountains, clouds, trees, blood vessels all exhibit fractal geometry. Fractals are characterized by fractional dimensions. A coastline is more than one-dimensional but less than two-dimensional. Its dimension depends on how convoluted it is. Fractals appear naturally in chaotic systems, in phase transitions, in the boundaries of basins of attraction. They're a signature of complexity, of systems operating at the edge of order and disorder. Let's talk about criticality and self-organized criticality. Some systems naturally evolve toward a critical state, a tipping point where small events can trigger large avalanches. Sand piles exhibit this. Add grains of sand one at a time, and most of the time, nothing happens. But occasionally, a single grain triggers an avalanche that can be small or large, with no way to predict which. The system is at the edge of instability, poised between order and chaos. Self-organized criticality might explain many natural phenomena. Earthquakes follow power law distributions, where small quakes are common and large quakes are rare, but there's no characteristic scale. Forest fires, extinctions, solar flares all show similar patterns. The systems are self-organizing, evolving without external tuning toward a critical state where events of all sizes can occur. This might be a universal principle, a way complex systems naturally organize themselves. Now let's discuss cellular automata and the game of life. These are simple computational models where cells on a grid change state according to rules based on their neighbors. John Conway's game of life has just a few rules, but it produces incredibly complex behavior. Patterns emerge, grow, move, interact. Some patterns are stable. Some oscillate. Some travel across the grid like spaceships. And from these simple rules, you can build computers, self-replicating structures, even patterns that exhibit lifelike behavior. Cellular automata show that complexity doesn't require complicated rules. Simple rules, iterated over and over, can generate rich behavior. Some researchers think the universe might be a cellular automaton, a vast computational grid updating according to simple local rules. This is the computational universe hypothesis, and while it's speculative, it's a reminder that the substrate of reality might be simpler than we think. Let's explore Wheeler's concept of it from bit in more depth. John Wheeler proposed that every physical quantity derives from bits of information. The universe is not made of matter or energy but of information, of answers to yes or no questions. He famously said, "No phenomenon is a real phenomenon until it is an observed phenomenon." The act of asking questions, of measuring, of observing, brings reality into existence. This is the participatory universe, where observers are not passive witnesses but active creators. Wheeler's ideas have influenced developments in quantum information theory and holography. If the universe is fundamentally informational, then understanding physics is about understanding how information is processed, stored, and transformed. The laws of physics are rules for manipulating information. Matter and energy are emergent concepts, ways of organizing and describing the underlying information. This is a radical shift in how we think about reality, and it's gaining traction as physicists explore the connections between information, entanglement, and space-time. Now let's talk about the origin of life, not from a biological perspective, but from a physics and chemistry perspective. Life is a complex, far from equilibrium system that maintains itself by consuming energy. How did such systems arise? The classic Miller-Urey experiment in the 1950s showed that organic molecules, the building blocks of life, can form spontaneously from simple gases like methane, ammonia, and water vapor when you add energy in the form of lightning. The early Earth had all the ingredients, and given enough time, complex molecules formed, eventually leading to self-replicating systems. But there's a gap between simple organic molecules and the first living cells. How did metabolism arise? How did genetic information in the form of DNA or RNA come about? The RNA world hypothesis suggests that RNA came first. RNA can both store information like DNA and catalyze reactions like proteins, so it could have been the original molecule of life. Over time, DNA took over information storage because it's more stable, and proteins took over catalysis because they're more versatile. But the transition from non-life to life remains one of the great unsolved problems in science. Some researchers think life didn't start in a primordial soup, but in hydrothermal vents on the ocean floor. These vents provide energy in the form of chemical gradients, and they have porous rock structures that could have acted as templates for the first cells. Others think life started in shallow pools that dried and refilled, concentrating molecules and driving chemical reactions. We don't know where or how life began, but we know it's a natural process, a consequence of chemistry and thermodynamics. Given the right conditions, life emerges. Let's discuss the shadow biosphere hypothesis. This is the idea that there might be a second tree of life on Earth, organisms so different from known life that we haven't recognized them. All known life uses the same genetic code, the same set of amino acids, the same basic biochemistry. But what if there's an entirely separate origin of life, using different molecules, different chemistry, existing alongside us undetected? These organisms might live in extreme environments, deep underground or in acidic lakes, and we might have sampled them without realizing they're alive because we're looking for DNA and proteins, and they use something else. This is speculative, but it's not impossible. If life arose twice on Earth independently, it would tell us that life is easy, that it emerges readily wherever conditions allow. And it would give us a second example of biochemistry, expanding our understanding of what life can be. The search for a shadow biosphere is ongoing, and while we haven't found anything yet, the possibility remains open. Now let's explore alternative biochemistries in more depth. Silicon-based life is a classic science fiction idea, but is it plausible? Silicon is in the same column of the periodic table as carbon, so it forms similar bonds. But silicon-silicon bonds are weaker than carbon-carbon bonds, and silicon doesn't form long, stable chains the way carbon does. Silicon compounds are also less diverse. On Earth, silicon is everywhere, but life chose carbon. That suggests carbon is superior for biochemistry, at least in water-based solvents. But what about non-water solvents? Ammonia stays liquid at lower temperatures than water, and it's abundant in the outer solar system. Life based on ammonia biochemistry might exist on Titan or on icy moons like Europa or Enceladus. These organisms would operate at extremely low temperatures, with slow metabolism and long lifespans. They might be so different from Earth life that we wouldn't immediately recognize them as living. Methane is another possibility. Titan has lakes of liquid methane on its surface, and some scientists speculate that exotic life forms could exist there, using methane as a solvent instead of water. Such life would be based on entirely different chemistry, possibly using hydrogen bonds in place of covalent bonds, or exotic compounds we've never imagined. The universe might be teeming with life, but most of it might be so alien that we'd struggle to identify it. Let's discuss XNA, synthetic alternatives to DNA. Scientists have created artificial nucleic acids with different sugar backbones: threose nucleic acid, TNA, glycol nucleic acid, GNA, peptide nucleic acid, PNA, and others. These XNAs can store genetic information and undergo evolution through selection, just like DNA and RNA. Some XNAs are more stable than DNA, resistant to degradation by enzymes. This raises the possibility that life elsewhere in the universe might use XNA instead of DNA. It also suggests that we could engineer synthetic organisms with XNA genomes, creating a new domain of life that doesn't interact with natural organisms, a biological firewall. Synthetic biology is pushing the boundaries of what life can be. We've created bacteria with expanded genetic codes, using more than the standard 4 DNA bases. We've synthesized artificial cells from scratch, assembling membranes, ribosomes, and genetic material to create minimal life forms. And we've rewritten entire genomes, replacing natural DNA with synthetic versions. We're learning to design life, not just study it. This raises ethical questions, but it also opens incredible possibilities for medicine, materials science, and our understanding of biology. Now let's talk about Schrödinger's book, What is Life? Published in 1944. Schrödinger asked how living organisms maintain order despite the second law of thermodynamics, which says entropy should increase. He proposed that life feeds on negentropy, negative entropy, by consuming low-entropy food and expelling high-entropy waste. Life maintains itself far from equilibrium, creating and maintaining order by increasing the entropy of its surroundings. This insight influenced the development of molecular biology and the discovery of DNA. Schrödinger also speculated that genetic information might be stored in an aperiodic crystal, a molecule with irregular structure that encodes information. This was remarkably prescient. DNA is exactly that, a long molecule with irregular sequence encoding genetic information. Schrödinger's book inspired a generation of physicists to enter biology, leading to the molecular revolution of the mid-20th century. It's a reminder that physics and biology are not separate. Life is a physical phenomenon, governed by the same laws as everything else, just organized in exceptionally complex and beautiful ways. Let's explore dissipative structures in more detail. These are ordered patterns that emerge in systems far from equilibrium. Prigogine showed that when energy flows through a system, it can spontaneously organize into structures that maintain themselves by dissipating energy. Examples include convection cells, chemical oscillations like the Belousov-Zhabotinsky reaction, and biological systems. Life itself is a dissipative structure, maintaining order by consuming energy and producing entropy. The key insight is that order and entropy are not opposites. You can have both increasing simultaneously. Locally, in the living organism, entropy decreases as order is created. But globally, including the environment, entropy increases as required by the second law. Life doesn't violate thermodynamics. It exploits thermodynamics using energy gradients to build and maintain complexity. Now let's discuss fractals in nature. Coastlines are fractal. Measure them at different scales, and the length increases because you capture more detail. The Koch snowflake is a mathematical fractal with infinite perimeter but finite area, demonstrating how fractal dimensions work. Mountains, clouds, blood vessels all exhibit fractal structure. This isn't coincidence. Fractals arise naturally in growth processes, in erosion, in branching systems where efficiency favors self-similar structure. The fractal dimension of an object quantifies its complexity. A smooth curve has dimension 1. A surface has dimension 2. A fractal coastline has a dimension between 1 and 2, depending on how rough it is. The concept of fractal dimension extends our notion of geometry, allowing us to describe irregular shapes mathematically. It's a powerful tool for analyzing complex systems in nature. Let's talk about power laws and scale-free networks. Many natural phenomena follow power law distributions, where the probability of an event decreases as a power of its size. Earthquakes follow a power law. Small quakes are common, large quakes are rare, but there's no characteristic scale. The same applies to city sizes, wealth distributions, word frequencies, and many other systems. Power laws indicate scale invariance, a kind of self-similarity across scales. Scale-free networks are networks where the degree distribution, the number of connections per node, follows a power law. Most nodes have few connections, but a few hubs have many. The internet is a scale-free network. So are social networks, protein interaction networks, and many others. Scale-free networks are robust to random failures but vulnerable to targeted attacks on hubs. Understanding them helps us design better communication systems, predict disease spread, and analyze complex systems. Small world networks are another interesting class. These are networks where most nodes are not directly connected, but any two nodes can be reached through a small number of steps. The famous 6 degrees of separation idea is an example. Stanley Milgram found that any two people in the United States are connected by an average of 6 acquaintances. Small world networks combine local clustering with long-range connections, making them efficient for information transmission. The brain is a small world network. So is the global power grid. Understanding small world properties helps us design more efficient systems and understand how information spreads. Now let's discuss universality and critical phenomena. Near phase transitions, systems exhibit universal behavior that doesn't depend on microscopic details. Water boiling, magnets losing magnetization, superconductors transitioning, all show similar critical behavior described by the same mathematical exponents. This is universality, and it's one of the deepest principles in physics. It tells us that macroscopic behavior can be independent of microscopic details, that there are equivalence classes of systems that behave identically near critical points. Universality is connected to renormalization group theory, a mathematical framework that explains how physics changes as you zoom in or out. Near critical points, systems become scale invariant, looking the same at all scales. This is why critical systems often exhibit fractal structure. Renormalization group theory has applications far beyond phase transitions, in particle physics, cosmology, and beyond. It's a unifying principle that connects seemingly unrelated phenomena. Let's explore the concept of quantum biology more. For decades, biologists assumed quantum effects were irrelevant in living systems because they're too warm and wet. But recent experiments have found quantum coherence in biological processes. Photosynthesis uses quantum superposition to explore multiple pathways simultaneously, finding the most efficient route for energy transfer. This was discovered in photosynthetic bacteria and algae, and it's now thought to be widespread. Birds navigate using Earth's magnetic field, and the mechanism might involve quantum entanglement. Light hits molecules in the bird's eye, creating pairs of entangled electrons. The magnetic field affects the spins, altering chemical reactions that send signals to the brain. The bird literally sees the magnetic field as a pattern overlaid on its vision. This is speculation, but experiments support it. Quantum tunneling plays a role in enzyme catalysis. Protons and electrons can tunnel through energy barriers, speeding up reactions that would be impossible classically. This might be essential for metabolism, allowing reactions to occur at body temperature that would otherwise require much higher energies. Quantum effects in biology are not just curiosities. They might be essential for life. Now let's talk about the orchestroar theory of consciousness in more depth. Penrose argues that consciousness involves a quantum process because it exhibits non-computational aspects. He believes that understanding is not algorithmic, that consciousness involves something beyond computation. This is controversial. Most neuroscientists and AI researchers think consciousness will be explained through classical computation, complex but ultimately reducible to algorithms. Penrose disagrees, and he points to Gödel's incompleteness theorems as evidence that human understanding transcends formal systems. Whether or not orchestroar is correct, it's raising important questions about the relationship between physics and consciousness. If consciousness is quantum, it might explain qualia, the subjective feel of experiences, and it might connect mind to the fundamental structure of reality. If consciousness is classical, it's still an emergent phenomenon that we don't fully understand. Either way, consciousness remains one of the deepest mysteries in science. Let's explore the anthropic principle from yet another angle. The strong anthropic principle has a teleological flavor, suggesting that the universe exists for observers. This is uncomfortable for many scientists because it seems to invoke purpose, and science traditionally avoids teleological explanations. But maybe there's a way to make sense of it without invoking purpose. If the universe is fundamentally quantum, and observation is what makes possibilities definite, then observers might play a necessary role in reality. Not because the universe was designed for them, but because observation is part of the structure of quantum mechanics. This is Wheeler's participatory anthropic principle again, and it's deeply connected to the interpretation of quantum mechanics. If many worlds is correct, observers don't play a special role. Every outcome happens. But if some version of Copenhagen or objective collapse is correct, then observation might be fundamental, and the universe might genuinely require observers to be fully real. We don't know which interpretation is correct, so the question remains open. Finally, let's return to the biggest question of all. Why does the universe exist? Why is there something rather than nothing? This is the ultimate mystery, the question that science might never answer. Some philosophers argue it's a meaningless question, that existence doesn't require explanation. Others think it's the most important question, the one that drives all inquiry. One answer is the anthropic principle. If there were nothing, there'd be no one to ask the question. We exist, so something must exist. But this feels like a tautology. Another answer is that the universe is necessary, that its existence is a logical necessity, like mathematical truths. But why should physical existence follow from logical necessity? Another answer is that the universe created itself, emerging from nothing through quantum tunneling or some other process. But even this requires laws of physics, and where do they come from? Maybe there is no ultimate answer. Maybe the universe is a brute fact, something that just is without explanation. Or maybe the answer lies in a deeper theory we haven't discovered yet, a theory that unifies all of physics and explains why this particular universe, with these particular laws, exists. We don't know, and maybe that's okay. The mystery is what drives us forward, what keeps us asking questions, seeking deeper understanding. Conclusion: we've journeyed even further into the cosmos, exploring quantum mysteries, black hole paradoxes, the nature of information and computation, the origins of complexity and life. We've seen that reality is stranger than we ever imagined, that the universe operates on principles that challenge our intuition and expand our minds. We've learned that space might emerge from entanglement, that information might be fundamental, that consciousness might connect to quantum mechanics, that life is a dissipative structure maintaining order in a universe trending toward chaos. Every theory we've explored raises new questions. Every answer leads to deeper mysteries. That's the nature of science. It's not about finding final answers. It's about expanding the frontier of knowledge, pushing back the darkness, uncovering the hidden patterns that govern reality. And the journey never ends. There's always more to discover, always deeper levels to explore. We're living in an extraordinary time. We've mapped the cosmic microwave background, detected gravitational waves, imaged black holes, created quantum computers, synthesized life in laboratories, and begun to understand consciousness. The next century will bring even greater breakthroughs. We'll solve mysteries that seem intractable today. We'll ask questions we can't even formulate yet. And future generations will look back at our era as the time when humanity truly began to understand the universe. But understanding requires more than intelligence. It requires humility, the recognition that the universe is under no obligation to make sense to us. It requires creativity, the ability to imagine possibilities beyond our experience. It requires courage, the willingness to question everything, even our most cherished beliefs. And it requires wonder, the childlike awe at the beauty and mystery of existence. So as we close this chapter of our cosmic journey, remember this. You're not just a collection of atoms. You're a pattern of information, a process, a way for the universe to know itself. Your thoughts, your experiences, your consciousness are part of the cosmos, as real and significant as stars and galaxies. You're made of stardust, animated by the same quantum processes that govern black holes and the Big Bang. You're connected to everything through the web of causality that stretches back to the beginning of time. And you have a choice. You can live your life without questioning, accepting the surface appearance of things. Or you can dive deeper, asking why, seeking understanding, participating in the grand adventure of discovery. You can be a passive observer, or you can be a co-creator of meaning in an otherwise meaningless universe. The cosmos doesn't care which you choose, but you should care, because in choosing to understand, to question, to wonder, you're fulfilling the highest potential of conscious existence. The universe is vast and ancient and strange. It contains wonders beyond imagination, mysteries that will take centuries to unravel, beauty that transcends words. And you're part of it. You're home. You always have been. And the adventure of understanding, the journey into the heart of reality, is just beginning. Welcome to the cosmos. The universe is waiting. And now, more than ever, we're ready to listen.